Welcome, we're so happy you tuned in tonight. Before we get started, I'd love to know, where are you watching from? Drop it in the comments. Now, let's get comfortable and drift into deep, peaceful sleep together. The ocean is Earth's oldest habit. It has been here longer than mountains, longer than forests, longer than almost anything else you can see or touch on the surface of the planet. It covers more than 70% of the globe, and it holds about 97% of all the water on Earth. But the ocean is not just a giant container filled with liquid. It is motion and chemistry and temperature and time, all moving slowly together. It is a body that breathes without lungs, circulates without a heart, and shapes the world without ever hurrying. Tonight, we're not here to learn quickly. We're here to drift, to let facts settle gently, one after another, like sand sinking through clear water. There is no urgency, no test, no need to hold on tightly to every detail. The ocean itself does not rush, and neither will we. If your mind wanders, let it. If your eyes grow heavy, let them. The ocean will still be here, moving in its patient way, long after you have drifted into sleep. Just one more small fact, and then we drift. Picture a calm, dark surface. Soft waves, steady breathing. The ocean at night is not dramatic. It does not crash or roar unless a storm passes through, and storms are rare compared to the endless stretches of stillness. Most of the time, the ocean is simply there, vast, quiet, holding the planet the way a blanket holds warmth. It is always in motion, but the motion is gentle. Water moves in currents that flow like slow rivers. It rises and falls with the tides, pulled by the moon. It evaporates into the air and returns as rain. It is a cycle, a rhythm, a pattern that has been repeating for billions of years. Let us begin with the simplest question. What is the ocean made of? The answer is mostly water, of course, but not pure water. Seawater is a solution, a mixture of water and dissolved substances. The most abundant of these substances is salt. When we talk about salt in the ocean, we usually mean sodium chloride, the same kind of salt you might sprinkle on food, but there are other minerals dissolved in seawater as well. Magnesium, calcium, potassium, sulfate, and dozens of trace elements all float invisibly in every drop. The salt in the ocean comes from rocks and rivers, and it has been accumulating for a very long time. When rain falls on land, it is slightly acidic, and as it flows over rocks and soil, it slowly dissolves minerals. These minerals are carried by rivers into the sea. Once in the ocean, the water evaporates, but the salt does not. It stays behind, and over millions and millions of years the ocean has become saltier. Not dramatically salty. Seawater is about 3.5% salt by weight, but enough to change the way it behaves. Saltwater freezes at a lower temperature than fresh water. Pure water freezes at 0 degrees Celsius, but seawater does not freeze until it reaches about -2 degrees Celsius. This is one reason why the ocean near the poles can remain liquid even in the coldest months, though. Sea ice does form when temperatures drop low enough. The ice that forms is less salty than the water it came from, because as water freezes, it tends to exclude the salt. This means that the water left behind becomes slightly saltier, slightly denser, and slightly more likely to sink. The ocean feels alive with chemistry even when it looks perfectly still. Oxygen dissolves in seawater, especially at the surface where waves mix air and water together. This dissolved oxygen is what allows fish and other marine creatures to breathe. Carbon dioxide also dissolves in seawater, and the ocean holds an enormous amount of it, far more than the atmosphere. This makes the ocean an important part of Earth's carbon cycle, absorbing carbon dioxide from the air and storing it in various forms for long periods of time. Temperature shapes the ocean in quiet, powerful ways. Sunlight warms the surface, but it does not penetrate very deep. The top layer of the ocean, warmed by the sun, can be quite comfortable, warm enough to swim in tropical regions. But below that warm surface layer, the temperature drops. There is often a boundary called the thermocline, a zone where temperature decreases rapidly with depth. Below the thermocline, the ocean is cold. Not freezing, but cold and steady, hovering just a few degrees above freezing no matter where you are on the planet. The deep ocean does not experience seasons. It does not warm in summer or cool in winter. It simply stays cold, patient, and dark. This layering of temperature is one reason the ocean is not a uniform soup. It is stratified, divided into zones based on temperature, salinity, and density. Warm water is less dense than cold water, so it tends to float on top. Salty water is denser than fresh water, so it tends to sink. These differences in density create structure, and structure influences how water moves. Just one more small fact, and then we drift. The ocean is mostly quiet mass. It does, not thrash or sprint. It holds more than 300 million cubic miles of water, and that water has weight and inertia. It takes time and energy to move it, and once it is moving, it takes time and energy to stop it. This is part of why the ocean is so steady, so calm in its core nature. Yes, there are waves on the surface, and yes, there are currents flowing through it, but these are small expressions of motion in an overwhelmingly large body. The ocean is not in a hurry. It measures time in centuries, in millennia, and ages. Now let us turn to motion. The ocean moves without hurry, and yet it is always moving. One of the most familiar motions is the tide. Twice a day in most places the ocean rises and falls. This is not because the ocean is breathing or because water is being added and removed. It is because the moon, and to a lesser extent the sun, are pulling on the water. Gravity is the key. The moon's gravity pulls on the earth, and because water is more fluid than rock, it responds more easily to that pull. The water on the side of the earth facing the moon is pulled slightly toward the moon, creating a bulge. At the same time, on the opposite side of the earth there is another bulge. This happens because the earth itself is also being pulled toward the moon. But the water on the far side is farther away from the moon and feels slightly less pull, so it lags behind, creating a second bulge. As the earth rotates, different parts of the coastline move through these bulges, and we experience this as high tide and low tide. The sun also affects the tides, though its effect is smaller because it is much farther away. When the sun, moon, and earth line up, during a new moon or a full moon, the sun's pull and the moon's pull work together, creating higher high tides and lower low tides. These are called spring tides, though they have nothing to do with the season. When the sun and moon are at right angles to each other, their pulls partially cancel out, creating smaller tidal ranges called neap tides. Tides are a slow-breathing pattern. They are predictable, rhythmic, and ancient. Long before humans built clocks, the tides kept time. Sailors learned to read them, to wait for high tide to enter a harbour, or to leave on an outgoing tide. Even today, the tides shape coastal life, when boats can launch, when certain animals feed, when sand is exposed or covered. But tides are not the only way the ocean moves. There are also currents, long invisible rivers inside the sea. Some currents flow near the surface, driven by wind. Others flow deep below, driven by differences in temperature and salinity. Together, these currents form a global circulation system that connects all the ocean basins. Surface currents are shaped by the wind, but also by the rotation of the earth. When wind blows across the ocean, it drags the surface water along with it. But the water does not move in exactly the same direction as the wind. Because the earth is rotating, the moving water is deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This effect is called the Coriolis effect, and it helps create the great loops of surface currents that circle the ocean basins. In the North Atlantic, for example, there is a current system called the North Atlantic Gyre. Warm water flows from the equator up along the coast of North America as the Gulf Stream, then continues northeast across the Atlantic toward Europe. As it cools, it turns southward, flowing down along the coast of Africa before curving back west toward the equator. This loop is thousands of miles across and flows continuously, moving warm water poleward and cool water equatorward. The Gulf Stream itself is a remarkable current. It is narrow, only about 60 miles wide in places, but deep and fast, carrying more water than all the rivers on Earth combined. It flows at several miles per hour, which may not sound fast, but for an ocean current it is brisk. The warmth it carries northward moderates the climate of Western Europe, making places like Ireland and the United Kingdom much milder than other regions at the same latitude. Surface currents like the Gulf Stream are important for moving heat around the planet. The sun warms the equator more than the poles, and without some way to redistribute that heat, the tropics would grow hotter and the poles would grow colder. Ocean currents, along with atmospheric winds, help balance the temperature, carrying warmth from the equator toward the poles and returning cooler water back toward the tropics. But not all currents flow at the surface. Some of the most important currents flow deep in the ocean, far below where wind or sunlight can reach. These deep currents are driven by differences in density, which in turn are driven by differences in temperature and salinity. This process is sometimes called thermohaline circulation, from the Greek words for heat and salt. Here is how it works. In the polar regions, especially near Greenland and Antarctica, the surface water becomes very cold. Cold water is denser than warm water. At the same time, when sea ice forms, it leaves behind saltier water, which is also denser. This cold, salty water sinks. It sinks all the way to the ocean floor and then it begins to flow. It flows along the bottom of the ocean, creeping slowly across the seafloor, moving from the poles toward the equator. This deep water can take hundreds or even thousands of years to complete its journey. It flows through the deep basins of the Atlantic, then loops around the southern tip of Africa and enters the Indian and Pacific Oceans. Eventually it rises back to the surface in certain regions, warmed by the sun and mixed back into the surface circulation. The entire loop of sinking, flowing, rising and returning is called the global ocean conveyor belt, and it is one of the slowest, steadiest circulations on Earth. Just one more small fact, and then we drift. Understanding currents helps us see the ocean not as a static pool, but as a body in constant quiet motion. Warm water tends to ride higher, cold, salty water tends to sink, and the planet's rotation helps steer everything into broad looping paths. These currents shape climate, influence weather, and create invisible highways that marine life has learned to navigate. There are also smaller, temporary currents caused by local conditions. Wind can pile water up against a coast, and when the wind stops, the water flows back out in a current. Tidal currents flow in and out of bays and estuaries as the tide rises and falls. Near the equator, there are currents that oscillate back and forth across the Pacific in patterns that influence weather worldwide. One of these patterns is called El Niño, a periodic warming of the central and eastern Pacific that can shift rainfall, droughts, and storms across entire continents. Sailors once relied on ocean currents like maps made of water, before engines, before satellites, before GPS. Knowing the currents meant the difference between a quick voyage and a slow, dangerous one. Ships travelling from Europe to the Americas learned to catch the westward flowing currents near the equator, then ride the Gulf Stream back home. These routes were traced and retraced, generation after generation, as reliable as roads. Even today, currents matter. They influence shipping routes, fishing grounds, and the spread of nutrients. They carry warmth and cold, oxygen and carbon, salt and fresh water. They connect distant parts of the ocean, making it not a collection of separate seas, but a single, interconnected body of water. Why do some coasts feel cooler than others, even at the same latitude? Often, it is because of currents. A cold current flowing along a coastline will keep the air above it cool, and when that cool air drifts over land, it brings fog and mild temperatures. The coast of California, for example, is cooled by the California Current, which flows southward from the North Pacific. In summer, when the land heats up, the cool ocean air creates fog that rolls in over coastal cities. The same principle applies in other regions. Where cold currents flow, coasts tend to be cooler and often foggier. The ocean's surface is not uniform, it has texture. There are regions where currents converge, pushing floating debris and plankton into long lines. There are regions where water upwells from below, bringing nutrients to the surface and creating rich feeding grounds for fish and seabirds. There are gyres where water circulates slowly, accumulating whatever floats and does not sink. The ocean is not just deep and wide, it is patterned, layered, and full of subtle structure. Just one more small fact, and then we drift. Now let us drift downward, peacefully, not with fear, but with curiosity. The deep ocean is not a dangerous void. It is simply different. It is a place where pressure increases, where darkness is complete, and where the rules of life take on new forms. Pressure in the ocean increases with depth. For every 10 meters you descend, the pressure increases by about 1 atmosphere, the same pressure you feel at sea level. At 100 meters deep, the pressure is 10 times greater than at the surface. At 1,000 meters, it is 100 times greater. At the deepest point in the ocean, the Mariana Trench, the pressure is more than 1,000 times what we experience on land. But pressure is not crushing in the way we might imagine. It is simply force evenly distributed. Creatures that live in the deep ocean have bodies adapted to that pressure. They do not feel crushed because the pressure inside their bodies matches the pressure outside. There are no air pockets to collapse, no rigid structures to buckle. The deep ocean is not hostile to life. It is simply a different kind of home. Darkness is another defining feature of the deep. Sunlight does not penetrate far into the ocean. The surface is bright, lit by the sun, and the top layer, perhaps the first 10 or 20 meters, is warm and well lit. Below that, light fades. By about 200 meters, there is very little light left. By 1,000 meters, it is completely dark, a darkness so total that no human eye could detect even a glimmer. This means that the deep ocean is a world without seasons, without day or night in the way we know them. There is no sunrise to wake to, no sunset to mark the end of the day. Time passes, but it is measured differently, by currents, by the slow drift of food from above, by the patient rhythms of life adapted to the dark. The seafloor is not flat. If you could drain the ocean and walk across the bottom, you would find mountain ranges taller than the Himalayas, valleys deeper than the Grand Canyon, volcanoes, ridges, plains, and plateaus. There are underwater mountain ranges called mid-ocean ridges, where tectonic plates pull apart and new seafloor is formed. There are trenches where one plate dives beneath another, descending into the Earth's mantle. There are seamounts, underwater mountains that rise from the seafloor but do not quite reach the surface. Some of these seamounts are extinct volcanoes worn smooth by the slow passage of time. The mid-ocean ridges are some of the longest mountain ranges on Earth, stretching for tens of thousands of miles through the Atlantic, Pacific, and Indian Oceans. They are not sharp, jagged peaks, but broad, gentle rises with a rift valley running down the centre. At the rift, hot magma wells up from below, cools, and solidifies into new rock. This process, called seafloor spreading, pushes the older rock outward, slowly widening the ocean basin. It is one of the ways the Earth renews itself, creating new crust in some places while destroying old crust in others. Trenches are the deepest parts of the ocean. The Mariana Trench in the Western Pacific reaches a depth of nearly 11,000 meters, almost 7 miles. If you placed Mount Everest at the bottom of the trench, its peak would still be more than a mile underwater. Trenches are formed where tectonic plates collide, and one plate is forced beneath the other in a process called subduction. They are narrow, steep-sided and cold, and they mark the zones where the ocean floor is being pulled back into the Earth. Between the ridges and the trenches lie the abyssal plains, vast flat regions of seafloor covered in fine sediment. These plains are some of the flattest places on Earth, stretching for hundreds or thousands of miles with barely any change in elevation. The sediment is made of tiny particles, dust blown from land, the remains of microscopic sea creatures, volcanic ash, and bits of rock carried by currents. It settles slowly, accumulating over millions of years, layer upon layer, like snow drifting onto a quiet field. Sound travels differently in water than in air. In air, sound moves at about 340 meters per second. In water, it moves more than 4 times faster, about 1,500 meters per second. This means that sound can travel long distances underwater. Whales use this to their advantage, sending low-frequency calls across entire ocean basins to communicate with one another. A whale's song, sung off the coast of one continent, can be heard thousands of miles away by another whale. The deep ocean is cold and stable. While the surface may warm and cool with the seasons, the deep ocean remains at a nearly constant temperature, just a few degrees above freezing. This stability makes it a refuge for creatures that prefer consistency. There are no sudden temperature swings, no storms to disrupt the quiet. Life in the deep is slow, patient, and finely tuned to the conditions. One of the most remarkable discoveries in deep-sea exploration was the finding of hydrothermal vents, places where hot, mineral-rich water pours out of cracks in the seafloor. These vents form along the mid-ocean ridges where seawater seeps into the crust, is heated by magma below, and then shoots back out through chimney-like structures. The water can be hundreds of degrees Celsius, hot enough to boil on the surface, but under the immense pressure of the deep ocean, it remains liquid. Around these vents, entire ecosystems have formed, relying not on sunlight but on the chemical energy in the vent fluids. Bacteria use a process called chemosynthesis to convert the chemicals, mostly hydrogen sulfide, into energy. These bacteria form the base of the food web, supporting communities of tube worms, clams, shrimp and crabs. It was a revelation when these ecosystems were first discovered in the late 1970s because it showed that life does not always need sunlight. It can thrive in total darkness, in extreme heat and pressure, sustained by chemistry alone. Just one more small fact, and then we drift. The deep ocean is not empty. It is quiet, slow, and spacious, but it is full of life. There are fish with enormous eyes adapted to catch the faintest glimmers of light. There are fish with no eyes at all, navigating by touch and vibration. There are jellyfish that pulse gently through the dark, translucent and fragile. There are squid that hunt in the twilight zone, the region between the sunlit surface and the pitch-black deep. There are creatures with bodies so soft they seem almost liquid, perfectly suited to the pressure and the stillness. Let us rise now, gently, back toward the light, and talk about ocean life as soft wonder. Life in the ocean comes in every imaginable form, from the smallest drifting bacteria to the largest animals ever to exist, and much of it is quiet, beautiful, and perfectly adapted to the world it inhabits. Plankton are the drifters. The word comes from the Greek word for wanderer, and it describes organisms that float or drift with the currents, unable to swim strongly against them. Plankton include both plants and animals. Phytoplankton are microscopic photosynthetic organisms, mostly single-celled algae, that float near the surface where sunlight can reach them. They are so small that a single drop of seawater can contain thousands of them, and they are so abundant that they produce more than half of the oxygen in Earth's atmosphere. Every other breath you take you owe to phytoplankton. Zooplankton are the animal counterpart. They include tiny crustaceans, larval forms of fish and invertebrates, and other small creatures that drift with the currents. Some zooplankton eat phytoplankton, others are predators, hunting other zooplankton. Together, phytoplankton and zooplankton form the base of the ocean's food web. Almost everything else in the ocean depends on them directly or indirectly. The great whales, the fastest fish, the sprawling kelp forests, all of it traces back to these tiny drifting organisms. One of the most enchanting features of ocean life is bioluminescence, the ability to produce light. In the deep ocean, where sunlight never reaches, many organisms have evolved the ability to glow. They produce light through chemical reactions, usually involving a molecule called luciferin and an enzyme called luciferase. When these substances combine in the presence of oxygen, they emit a soft, cold light, blue or green usually, because those colours travel farthest in water. Bioluminescence is used for many purposes. Some creatures use it to attract prey, dangling a glowing lure in the darkness to tempt smaller animals close. Others use it to communicate, flashing patterns to signal mates or warn rivals. Some use it for camouflage, producing light on their undersides to match the faint glow of sunlight from above, making themselves invisible to predators looking up from below. And some use it defensively, releasing clouds of glowing fluid to startle or confuse attackers. The effect is like underwater starlight. Imagine sinking into the dark ocean, and as your eyes adjust, you begin to see soft pulses of blue-green light, jellyfish drifting by, their bodies glowing faintly, tiny shrimp darting away in bursts of brightness, larger shapes outlined in luminous patterns. It is a quiet, peaceful display, not dramatic but steady, a reminder that even in the darkest places there is light. Coral reefs are slow-built cities. They are made of the skeletons of tiny animals called coral polyps. Each polyp is small, often just a few millimeters across, and it builds a cup-shaped skeleton of calcium carbonate around itself. When the polyp dies, the skeleton remains, and new polyps build on top of it. Over centuries and millennia, these skeletons accumulate into massive structures, reefs that can stretch for hundreds of miles. Coral reefs are among the most diverse ecosystems on Earth. Though they cover less than 1% of the ocean floor, they support about a quarter of all marine species. Fish, crustaceans, mollusks, sponges, sea stars, urchins, and countless other organisms live among the coral, finding shelter, food, and breeding grounds. The structure of the reef creates endless nooks and crannies, each one a potential home. The corals themselves are not just rock. The living polyps have a symbiotic relationship with microscopic algae called zooxanthellae, which live inside the coral tissue. The algae photosynthesize, producing food for the coral. In return, the coral provides a safe place to live and access to sunlight. This partnership is delicate. If the water becomes too warm or too polluted, the coral can expel the algae in a process called bleaching. Without the algae, the coral turns white and, if conditions do not improve, may die. Reefs grow slowly. A coral colony might grow only a centimetre or two per year. Large ancient reefs may be thousands of years old, built layer upon patient layer. They are monuments to slow, steady growth, to the accumulation of small efforts over long time. Kelp forests are another kind of underwater forest, found in cooler coastal waters. Kelp is a type of large brown algae, and the fastest growing forms can grow more than 0.5 metre per day in ideal conditions. Kelp anchors itself to the seafloor with a root-like structure called a holdfast, and from there it sends up long, flexible stipes that rise toward the surface. At the top, broad blades spread out to catch sunlight, and gas-filled bladders help keep the kelp upright. A kelp forest sways with the current, bending and flowing like tall grass in the wind. Light filters down through the blades, creating dappled patterns on the seafloor. Fish weave between the stipes. Sea otters wrap themselves in kelp fronds to keep from drifting away while they sleep. The kelp softens the force of waves, creating calmer water behind it and protecting the shore from erosion. Kelp is food for many animals. Sea urchins graze on it, and if their populations grow too large, they can clear entire kelp forests, turning them into barren rock. But where predators like sea otters keep the urchins in check, the kelp thrives, creating a rich, productive ecosystem. Migration is one of the ocean's quiet wonders. Many marine animals travel vast distances, following seasonal patterns, food sources, or the pull of instinct. Grey whales migrate from the cold waters of the Arctic to the warm lagoons of Baja California to give birth, a journey of more than 10,000 miles round trip. They travel slowly, staying close to the coast, and they do this every year. Sea turtles navigate across entire ocean basins, sometimes travelling thousands of miles, to return to the very beach where they were born. How they find their way is still not entirely understood. They may use the Earth's magnetic field, the angle of the sun, the taste of the water, or some combination of cues. Whatever the method, it works. Year after year, turtles return to the same beaches, dig nests in the sand, lay there, eggs, and then swim back out to sea. Fish migrate too. Salmon are born in freshwater streams, swim downstream to the ocean, spend years feeding and growing in the open sea, and then return to their home stream to spawn. They navigate upstream, against the current, sometimes leaping over waterfalls and obstacles, driven by an urge that has shaped their species for millennia. Even tiny plankton migrate, though their journey is vertical rather than horizontal. Many zooplankton spend the day in the deep, dark water where they are safer from predators. At night, they swim upward toward the surface to feed on phytoplankton. This daily journey, repeated by countless billions of individuals, is one of the largest movements of biomass on the planet. Schools of fish move like living brushstrokes. Thousands or even millions of individuals swim together, turning in unison, creating shapes that flow and shift. Each fish follows simple rules. Stay close to your neighbours, match their speed, avoid collisions, and from these simple rules, complex coordinated behaviour emerges. A school can confuse predators, making it hard to single out one individual. It can also make finding food easier, as many eyes are better than one. Even the strangest creatures of the deep are calm solutions to deep water living. The anglerfish, with its glowing lure and enormous mouth, is not a monster, but a patient hunter, waiting in the dark for prey to come within reach. The giant squid, with the eyes the size of dinner plates, is not a terror, but a deep-sea predator adapted to see in near-total darkness. The gulper eel, with its huge hinged jaw, is designed to swallow prey larger than itself, a useful trait in a place where meals are rare and unpredictable. Life in the ocean is efficient, quiet, and perfectly adapted. There is no wasted motion, no drama, just the slow unfolding of survival and reproduction over millions of years. Just one more small fact, and then we drift. Now let us zoom out, still soothing, and see the ocean as part of the whole planet. The ocean is not separate from the land, the air, or the sky. It is connected to everything, shaping weather and climate, feeding the water cycle and influencing the very composition of the atmosphere. The ocean stores and moves heat. It absorbs sunlight, especially in the tropics, and because water has a high heat capacity, it can hold that warmth for a long time. Currents carry the warm water poleward, releasing heat into the atmosphere as they go. This helps moderate the planet's climate, keeping the tropics from overheating and the poles from becoming even colder. The ocean also stores heat in deeper layers. When the surface warms, some of that heat is mixed downward by waves and currents. The ocean holds far more heat than the atmosphere, about 1,000 times more in fact. This makes it a buffer, absorbing excess heat and releasing it slowly over time. Without the ocean, the Earth's climate would be much more volatile, swinging between extremes. Evaporation from the sea is the beginning of the water cycle. The sun warms the ocean surface, and water molecules escape into the air as vapor. This vapor rises, cools, and condenses into clouds. The clouds drift over land, and the water falls as rain or snow. The rain feeds rivers, lakes, and groundwater, which eventually flow back to the sea, completing the cycle. Most of the rain that falls on land comes from water that evaporated from the ocean. In this way, the ocean is the source of almost all fresh water. It is the planet's great reservoir, constantly giving up water to the sky and receiving it back over and over in a rhythm that has been going on for as long as there has been liquid water on Earth. Sea ice and salty water affect circulation in subtle but important ways. When sea ice forms in polar regions, the water left behind becomes saltier and denser. This dense water sinks and drives deep ocean currents, which in turn help distribute heat and nutrients around the globe. If the formation of sea ice slows or stops, the circulation can weaken, which can have far-reaching effects on climate and ocean ecosystems. Coastal air often carries the ocean's fingerprint. If you live near the coast, you may have noticed that the air feels different, often cooler in summer, milder in winter, and more humid year-round. This is because the ocean moderates temperature. Water heats and cools more slowly than land, so the ocean acts as a thermal buffer, keeping coastal regions from experiencing the extremes that inland areas do. The smell of the sea is real, and it comes from chemicals produced by marine organisms. One of these chemicals is dimethyl sulfide, produced by phytoplankton. When it evaporates into the air, it gives the ocean its characteristic scent. This scent is not just pleasant, it also plays a role in cloud formation. Dimethyl sulfide can act as a nucleus for water vapor to condense around, helping to form clouds over the ocean. The ocean is distant but not separate from you. The water in your body, about 60% of your mass, echoes the planet's water cycle. You drink water that once evaporated from the sea, fell as rain, flowed through rivers, and was purified for your use. You breathe out water vapor with every breath. You sweat and the water evaporates, returning to the air. Salt helps your nerves and muscles work. Your cells are bathed in a salty fluid, not unlike seawater in its composition, though much less concentrated. This is a reminder that life began in the ocean, billions of years ago, and that even now, landlocked and far from the coast, we carry the ocean's chemistry inside us. The ocean's chemistry is vast and complex. It absorbs carbon dioxide from the air, which reacts with seawater to form carbonic acid. This makes the ocean slightly acidic, though still on the basic side of the pH scale. The ocean can absorb enormous amounts of carbon dioxide, which has been important in regulating Earth's climate over geological time. However, the rate at which carbon dioxide is currently being added to the atmosphere is faster than the ocean can easily absorb, and this is causing changes in ocean chemistry that scientists are still studying. The ocean influences weather in direct and indirect ways. Hurricanes and typhoons form over warm ocean water, drawing energy from the heat stored in the sea. The evaporation of ocean water adds moisture to the atmosphere, which can fuel storms. Ocean currents can steer weather patterns, guiding storms along certain paths or blocking them from others. El Niño, mentioned earlier, is a pattern of warming in the central and eastern Pacific that occurs every few years. When it happens, it can shift rainfall patterns across the globe. Some regions that are normally dry receive heavy rains. Others that are normally wet experience drought. Fisheries can be affected, as the warm water disrupts the usual upwelling of nutrients. The effects of El Niño can last for months, demonstrating how changes in the ocean can ripple through the entire climate system. Even the quiet sea is never truly still. There is always some motion, currents flowing, tides rising and falling, waves travelling across the surface. Energy is always passing through the water, even when it looks calm. This constant, gentle motion is part of what makes the ocean feel alive. Just one more small fact, and then we drift. Now we come to the slowest perspective, the deepest time. The ocean has not always looked the way it does today. Over hundreds of millions of years, continents have drifted, collided, and split apart. Shorelines have wandered, ocean basins have opened and closed, and through it all, the ocean has kept moving. Patient, steady, unbothered. 300 million years ago, the continents were joined together in a supercontinent called Pangaea. The ocean that surrounded it was called Panthalassa, and it was vast, far larger than any ocean today. Over time, Pangaea broke apart and the pieces drifted slowly across the globe. As the continents moved, new ocean basins opened between them. The Atlantic Ocean, for example, is relatively young. It began to form about 200 million years ago, as North and South America separated from Europe and Africa. The ocean floor is constantly being renewed. New crust forms at the mid-ocean ridges, and old crust is pulled back into the earth at the trenches. This means that the oldest seafloor is only about 200 million years old, which is young compared to the age of the Earth. The ocean water itself is much older, billions of years, but the floor beneath it is constantly recycled. Currents have rearranged over time as continents have shifted. The opening or closing of a seaway can redirect entire current systems. For example, the formation of the Isthmus of Panama about 3 million years ago closed the connection between the Atlantic and Pacific Oceans. This forced currents to reroute, which may have strengthened the Gulf Stream and influenced the climate of the Northern Hemisphere. Sea level has risen and fallen many times. During ice ages, when vast amounts of water were locked up in glaciers, sea level was much lower than it is today, sometimes more than 100 meters lower. Shorelines extended far beyond where they are now. Land bridges appeared, connecting continents and allowing animals to migrate. When the ice melted, sea level rose again, flooding coastal areas and creating new coastlines. The ocean has witnessed the rise and fall of countless species. It has been home to trilobites, ammonites, ancient sharks, marine reptiles, and countless others. Some of these lineages have gone extinct. Others have evolved into the creatures we see today. The ocean is a museum of life, a place where evolution has been unfolding for more than 3 billion years. Waves are just energy passing through water. When you watch a wave, it looks like the water is moving forward, but mostly it is not. The water molecules move in small circles, up and down and forward and back, returning close to where they started. It is the energy that moves forward, travelling across the surface until it reaches the shore where it is finally released. Waves are created by wind. The stronger the wind, the longer it blows, and the greater the distance it blows over, called the fetch, the larger the waves become. In the open ocean, waves from different storms can overlap, creating complex patterns. Some waves travel thousands of miles from their point of origin, crossing entire ocean basins before reaching a distant shore. When waves approach the shore, they begin to interact with the seafloor. The bottom of the wave drags on the sand or rock, slowing it down, while the top continues forward. Eventually, the wave becomes too steep and breaks, releasing its energy onto the beach. This breaking is not violent or angry. It is simply energy finding its release. Tides keep time without clocks. They do not need batteries or winding. They are driven by the steady pull of the moon, which itself is locked in orbit around the Earth. The moon's orbit is slow and predictable, and so are the tides. For as long as the moon orbits the Earth, the tides will continue. Even in the quietest parts of the ocean, far from shore, far from storms, there is motion. Deep currents creep along the seafloor. Plankton drift with the slow circulation. Heat diffuses through the water, molecule by molecule. The ocean is never frozen in place. It is always adjusting, always responding to the subtle forces acting on it. The ocean has been moving for billions of years. It has circulated through ice ages and warm periods, through extinctions and explosions of life, through the slow drift of continents and the reshaping of the Earth's surface. It has been patient through all of it, neither rushed nor delayed, simply moving at its own pace. Tonight, you do not need to carry thoughts. You do not need to remember every fact. understand every process, or hold on to every detail. The ocean carries motion for the whole planet. It moves heat, water, nutrients, and life. And it does so without effort, without strain, without needing to think about it. It simply is. Your body too knows how to move without thinking. Your heart beats, your lungs breathe, your blood circulates. These are rhythms you do not control, and you do not need to. They happen on their own, just as the ocean's currents flow on their own, just as the tides rise and fall on their own. Sleep is your body's way of doing the same thing the ocean does, restoring, resetting, and letting the next gentle moment arrive. You do not have to force it. You do not have to worry about it. You simply let go and let the natural rhythms take over. Just one more small fact, and then we drift. The ocean is still out there, moving in the dark. Tides are shifting. Currents are flowing. Waves are travelling across open water. Plankton are drifting. Deep-sea creatures are gliding through the black. The ocean is doing what it has always done, and it will continue to do so long after this night has passed. You are safe. You are still. You are supported like water floating on denser water, like a surface layer warmed by the sun. You do not need to hold yourself up. You can let the world carry you, just as the ocean carries everything within it. Breathe slowly like the tide coming in. Hold for a moment, like the high water resting at the shore. Breathe out, like the tide retreating. Hold for a moment, like the stillness between breaths. And again, in, hold, out, hold. Slow and steady, no effort, just the natural rhythm of air moving in and out of your body. The ocean does not hurry. It has no deadlines, no appointments, no urgency. It simply is, and it moves in its own time. You can do the same. There is nowhere you need to be, nothing you need to do, no thought you need to hold. The ocean has been moving for billions of years, and sleep is your body's way of joining that rhythm, restoring, resetting, and letting the next gentle moment arrive. Just one more small fact, and then we drift. The ocean is patience itself. It shapes coastlines one grain of sand at a time. It wears down cliffs over millennia. It carries sediment from one side of the planet to the other, slowly, grain by grain. There is no rush. There is only the steady, unending motion. And you tonight can be just as patient with yourself. You do not need to fall asleep quickly. You do not need to force anything. You can simply rest, breathe, and let the gentle facts settle in your mind like sediment drifting to the seafloor. Some will stay, some will dissolve. It does not matter. What matters is the calm, the stillness, the quiet sense that everything is moving as it should. The ocean holds the planet, and tonight you can let go knowing that the world will keep turning, the tides will keep shifting, and the gentle rhythms of water and air and life will continue steady and sure while you rest. Just one more small fact, and then we drift. The next story is about to begin. Please relax and enjoy. A dream is a conscious experience that happens while the body is asleep. It sounds simple when you say it that way, but even that basic definition opens a quiet door into something strange and beautiful. Right now, as you settle into this moment, your brain is preparing for the same nightly journey it has taken thousands of times before. Dreams are part of that journey. They arrive without asking permission, unfold according to their own logic, and then fade away like breath on a cold window. You don't have to do anything to make them happen. You don't have to understand them. You can simply let them be what they are, images and sensations that pass through the night while your body rests. When we talk about dreams, we're talking about more than just pictures in your mind. Dreams can include images, yes, but they can also include sounds, emotions, and even physical sensations. You might hear music in a dream, or the sound of rain, or a voice you recognize. You might feel the texture of sand under your feet, or the weight of a blanket, or the sensation of moving through water. You might feel joy or confusion, or a kind of peaceful curiosity. Dreams are rich experiences, built from the same sensory and emotional materials that make up your waking life. The brain doesn't stop creating experience just because your eyes are closed and your muscles are still. It keeps painting the world, just in a different key. Here's something that might surprise you. You can dream without remembering it afterward. Most people do this almost every night. The dreaming happens fully and completely, But when morning comes, there's no trace of it left in conscious memory. It's like watching a movie and then walking out of the theatre without being able to recall a single scene. The experience was real while it lasted, but it didn't get stored in the part of your memory that you can access later. This isn't a failure or a problem, it's just how the system works most of the time. Your brain is busy with other tasks during sleep, and holding on to every detail of every dream isn't always the priority. Dream recall is more likely if you wake up during or right after a dream. This is because the process of remembering a dream requires a brief moment of waking awareness to transfer those fragile images from short-term memory into something more stable. If you wake up in the middle of the night and find yourself thinking about a vivid scene or strange conversation, that's often because you woke right out of a dream. The images are still fresh, still glowing softly in your mind, and your waking brain has just enough time to catch them before they dissolve. But if you sleep straight through to morning without those little interruptions, the dreams you had earlier in the night might be completely gone, as if they never happened at all. Many dreams are short, even if they feel long. Time is strange in dreams. A dream that seems to last for hours might actually unfold in just a few minutes. The brain compresses experience, skips over the boring parts, and jumps from moment to moment without the slow, steady passage of time that defines waking life. You might dream about a long journey, but the dream itself doesn't include every step of that journey. It includes the important parts, the emotionally significant parts, and lets the rest fade into vague implication. This is part of why dreams feel so fluid and fast-moving. They're not bound by the same rules that govern your daytime experience of time. Dreams often borrow familiar places and rearrange them quietly. You might dream about your childhood home, but the rooms are in the wrong order, or there's a door that leads somewhere impossible. You might dream about your workplace, but it's somehow combined with a place you visited on vacation years ago. The brain is very good at taking pieces of real memory and blending them into new configurations. It's not trying to recreate reality exactly, it's trying to create something that feels real enough to hold your attention, to carry emotion, to serve whatever function the dream is quietly serving in the background. The settings in dreams are often like stage sets, convincing from the front, but not meant to be examined too closely. The brain can create faces by blending features it has seen before. This is one of the quiet marvels of dreaming. You might dream about someone you've never met, and they feel completely real, completely specific. But that face isn't invented from nothing. It's built from a library of faces your brain has encountered over the course of your life. A stranger in a dream might have your cousin's eyes, your dentist's nose, and the smile of someone you passed on the street years ago. The brain is an excellent collage artist, pulling from its vast collection of visual memories and assembling new combinations on the fly. You don't notice the seams. The person feels whole and real in the dream, even though they're a composite, a blend, a new arrangement of familiar parts. Dreams can feel meaningful, even when they're built from random fragments. This is one of the more interesting tensions in dream science. On one hand, many dreams seem to be constructed from arbitrary details, leftover images from the day, random firing of neurons, bits of memory that happen to be active at the same time. On the other hand, dreams often feel significant. They carry emotion. They seem to be about something, and even if the content is strange or illogical, the feeling of meaning can be very strong. Some scientists think this sense of meaning is something the brain imposes after the fact, a way of making sense of random activity. Others think dreams really are doing something important, even if we don't fully understand what that is yet. Both things can be true. A dream can be built from fragments and still carry emotional weight. The meaning doesn't have to be literal to be real. Dream logic often values feeling over accuracy. In a dream, you might accept things that would seem absurd if you were awake. You might fly or breathe underwater or find yourself in two places at once. You might talk to someone who's been dead for years, and in the dream, that feels perfectly natural. This isn't because you're confused, it's because the dreaming brain prioritizes emotional coherence over logical consistency. If something feels right in the dream, it is right, at least for the duration of that experience. The part of your brain that questions and analyzes and says, wait, that doesn't make sense, is quieter during sleep. The part that feels and imagines and flows from moment to moment is more active. So dream logic is a kind of emotional logic, where the rules are about meaning and feeling rather than physics and probability. Most people dream multiple times per night, even if they think they don't. This is one of those facts that can be surprising at first, but makes sense when you think about how sleep works. Sleep isn't one long, continuous state. It's a cycle that repeats several times, and dreams can happen in different parts of that cycle. You might have a dream early in the night, then fall into deeper sleep, then have another dream a few hours later, then another one near morning. Some of these dreams you'll remember, some you won't. But they're all there, quietly unfolding while your body rests and your conscious mind is offline. Even people who swear they never dream are dreaming. They're just not remembering it, which is completely normal and nothing to worry about. Just one more small fact, and then we drift. Sleep moves in repeating cycles through the night. Each cycle lasts about 90 minutes, give or take, and during that time your brain passes through different stages of sleep. These stages have different characteristics, different brainwave patterns, different purposes. The cycle starts with lighter sleep, descends into deeper sleep, and then rises back up, toward a lighter, more active stage before starting the whole process over again. You go through this cycle 4 or 5 times in a typical night, and each cycle is a little different from the one before. The first cycle of the night tends to have more deep sleep. The later cycles tend to have more of the lighter, dream-rich sleep. It's a rhythm, a gentle oscillation that carries you through the night. Dreams can happen in more than one sleep stage. For a long time, people thought dreams only happened during one specific stage of sleep, but we now know that's not quite right. Dreams can occur in several different stages, though the character of those dreams can vary depending on when they happen. The brain is always active during sleep, always processing, always generating some kind of internal experience. Sometimes that experience is vivid and story-like. Sometimes it's vague and thought-like. But it's all dreaming, in a broad sense. The brain doesn't fully shut down at night. It shifts into different modes, and dreams are part of those modes. REM sleep is famous for vivid dreaming. REM stands for rapid eye movement, and it's a stage of sleep that has some very distinctive features. During REM, your eyes move quickly back and forth under your closed eyelids. Your heart rate increases slightly, your breathing becomes more irregular, and your brain activity looks surprisingly similar to the brain activity of someone who's awake. This is the stage where the most intense, story-like, emotionally vivid dreams tend to happen. If you wake someone up during REM sleep and ask them what they were just experiencing, they'll usually be able to describe a detailed dream with characters, settings, and events. REM sleep is where the brain seems to be at its most creative, spinning out elaborate scenarios and complex narratives. Non-REM dreams can be calmer, simpler, and more thought-like. These are the dreams that happen in the other stages of sleep, the stages that aren't REM. Non-REM dreams are often less vivid, less visual, less story-driven. They might feel more like quiet thinking, or a series of impressions, or a vague sense of something happening without clear details. You might dream about a problem you're trying to solve, or a feeling you're trying to process without any specific imagery or plot. These dreams are still real dreams. They're just different in texture and tone from the big, vivid REM dreams. Some people actually prefer non-REM dreams because they're gentler, less demanding of attention, less likely to wake you up with strong emotion. Early night dreams often feel more grounded and practical. This has to do with the structure of sleep cycles. Early in the night, your brain is still processing the events of the day, sorting through recent memories, filing away information. The dreams that happen during this time tend to reflect that work. You might dream about something that happened earlier that day, or something you need to do tomorrow, or a conversation you had that's still lingering in your mind. These dreams are often less fantastical, more tied to real life. They feel like the brain is doing administrative work, organizing and categorizing rather than creating wild new scenarios. Late-night dreams often feel more vivid and story-like. As the night goes on and you move through multiple sleep cycles, the balance shifts. You spend less time in the deepest stages of sleep and more time in REM. Your dreams become longer, more detailed, more emotionally intense. This is when you're most likely to have those big, memorable dreams that you wake up thinking about. The dreams near morning are often the ones that stick with you because they're happening closer to the time you wake up, and because they're often more vivid and engaging than the dreams earlier in the night. If you remember a dream, there's a good chance it came from the last cycle or two of the night. REM periods tend to get longer toward morning. In the first sleep cycle of the night, you might only spend a few minutes in REM, but by the fourth or fifth cycle, you might spend 20 or 30 minutes in REM. This gradual lengthening means you're getting more and more dream time as the night progresses. It's one reason why sleeping in a little bit on a weekend morning can lead to especially vivid dreams. You're giving yourself more time in those long late-night REM periods, and that extra time translates into more elaborate dream experiences. Your brain doesn't turn off at night, it shifts into different modes. This is worth emphasizing because sometimes people think of sleep as a kind of shutdown, like turning off a computer. But the brain doesn't work that way. It's always active, always consuming energy, always doing something. During sleep, it's doing different kinds of work than it does during the day. It's consolidating memories, clearing out metabolic waste, strengthening connections between neurons, processing emotions. And part of that work involves generating dreams. Dreams aren't a malfunction or a random side effect. They're part of what the brain does when it's in sleep mode. Waking briefly between cycles is normal, even if you don't notice it. Most people wake up several times during the night, usually for just a few seconds or a minute or two. These micro-wakings often happen at the transition point between sleep cycles, when the brain is moving from one stage to another. You might open your eyes, shift position, and then fall back asleep so quickly that you have no memory of it in the morning. This is completely normal and healthy. It's not a sign of insomnia or poor sleep, it's just part of the natural rhythm of sleep. Sometimes these brief wakings are when you catch a glimpse of a dream before it fades. Other times you wake and fall back asleep without any dream memory at all. The calmer you feel, the easier it is to let dreams pass without clinging. This is something people often notice when they start paying attention to their relationship with dreams. If you wake up from a dream and immediately try to hold on to every detail, to analyze it, to figure out what it means, you can actually make yourself more wakeful. The effort of remembering and analysing pulls you further out of sleep. But if you wake from a dream and simply let it be there without grasping at it, it often just dissolves on its own, and you drift back into sleep easily. There's a kind of gentle acceptance that makes sleep smoother. You can acknowledge that you had a dream, maybe notice the general feeling of it, and then let it go. The dream has already done whatever work it was going to do. You don't need to chase it. Just one more small fact and then we drift. Forgetting dreams is common and normal. It's actually the default state for most people. We dream every night, often multiple times, but we remember only a tiny fraction of those dreams. This isn't a problem. It doesn't mean your dreams aren't important or that your sleep isn't working properly. It just means your brain is prioritizing other things. Dream memory is fragile, and it requires specific conditions to be preserved. Without those conditions, the dream simply fades, leaving no trace behind. You can go through your whole life dreaming every night and remembering only a handful of dreams. That's a perfectly normal, healthy way to experience sleep. Dream memories can fade quickly, like mist after sunrise. The comparison to mist is actually very apt. Dreams often feel vivid and real while they're happening, but the moment you wake up, they start to dissolve. Details blur, characters become vague. The plot that seemed so clear a moment ago becomes confusing and hard to follow. Within minutes, the dream might be completely gone. This rapid fading is characteristic of dream memory. It's different from other kinds of memory, which tend to be more stable. A dream is held in a very temporary, very fragile kind of storage, and unless it gets transferred to more permanent memory quickly, it just evaporates. Waking up suddenly can interrupt the process of saving the dream. When you wake up gradually, there's a brief transition period where you're partly asleep and partly awake, and during that transition, your brain has a chance to move the dream from very short-term storage into something a bit more lasting. But if you wake up suddenly, because of an alarm or a loud noise or someone calling your name, that transition gets disrupted. The dream is still there for a moment, but it's already starting to fade, and without that gentle transition time, it often fades completely before you can catch it. This is one reason why people who use alarms often remember fewer dreams than people who wake up naturally. The brain prioritizes waking life information over dream details. From an evolutionary perspective, this makes sense. Your brain needs to remember where you live, who your family is, what you did yesterday, what you need to do today. Those are survival-relevant memories. Dreams, on the other hand, are internal simulations. They're not real events. They didn't happen in the external world, so the brain tends to treat them as lower priority when it comes to long-term storage. There's only so much memory capacity available, and the brain has to be selective about what it keeps. Dreams, for the most part, don't make the cut. They serve their purpose in the moment, and then they're allowed to fade. Dream recall improves with gentle attention, not force. If you're interested in remembering your dreams, the best approach is a kind of soft, patient curiosity. You can set an intention before sleep, something like, "I'm open to remembering a dream tonight if one wants to be remembered." You can keep a notebook by your bed and jot down anything you recall when you wake up, even if it's just a vague impression or a single image. You can wake up slowly and lie still for a moment, giving yourself time to notice if there's any dream residue lingering. But trying to force it, or getting frustrated when you don't remember, usually backfires. Dream recall is a gentle skill, and it responds better to patience than to pressure. Writing a dream down quickly increases recall. This is one of the most reliable techniques for improving dream memory. If you wake up with a dream still fresh in your mind, and you take even just a minute to write down a few key words or images, you dramatically increase the chances that you'll be able to remember more of the dream later. The act of writing it down helps transfer the dream from that fragile temporary storage into something more stable. You're giving your brain a second exposure to the material, reinforcing the memory. Even a few scribbled notes on a bedside notepad can make the difference between remembering the dream in detail later and having it vanish completely by the time you get out of bed. Moving immediately after, waking can make recall fade faster. When you first wake up, if you lie still for a moment, you're more likely to hold on to dream memories. But if you immediately sit up, get out of bed, and start moving around, the dream tends to slip away more quickly. Physical movement seems to shift the brain into waking mode more fully, and that shift can overwrite the dream memory before it has a chance to solidify. This is why some people find that they remember dreams better if they wake up slowly and spend a few moments just lying there, letting their mind wander back over the experience they just had. Bright screens right after waking can overwrite dream memory. This is a more recent discovery, related to our modern habits of checking phones first thing in the morning. Bright light, especially blue light from screens, signals to your brain that it's time to be fully awake. And the flood of new information, messages, emails, news, social media, gives your brain something new to focus on. That new information can effectively push the dream memory out of the way. The dream was already fragile, and now it's competing with all this urgent, attention-grabbing waking world content. Usually the dream loses that competition. If you want to remember dreams, it's better to spend the first few moments of waking without looking at a screen, just letting your mind settle and noticing what's there. Emotional dreams are more likely to be remembered. This makes sense from a memory perspective. Emotion is a powerful memory enhancer. When something makes you feel strongly, your brain tags it as important and is more likely to store it long term. The same principle applies to dreams. If a dream makes you feel happy, or sad, or frightened, or excited, that emotional charge increases the likelihood that you'll remember it. A neutral dream, even if it's detailed and coherent, is more likely to fade. But a dream that carries strong emotion tends to stick around, at least for a while. This is one reason why nightmares are often remembered so vividly, even though they're not necessarily more frequent than other kinds of dreams. The fear or distress they cause makes them memorable. Even forgotten dreams can still affect mood in subtle ways. This is one of the stranger findings in dream research. Sometimes people wake up feeling a certain way, sad or anxious or inexplicably happy, without remembering any dream that would explain that feeling. But if you wake them during the night and ask about their dreams, it turns out they were having dreams with emotional content that matches their waking mood. The dream was forgotten, but the emotion lingered. It's as if the dream did some emotional work, processed some feeling, and then left behind an emotional residue without leaving behind the narrative or imagery. Your mood in the morning can sometimes be a clue to what you were dreaming about, even if you can't remember the dream itself. Just one more small fact, and then we drift. REM dreams often contain stronger emotions. When scientists study dream reports from people woken during REM sleep, they find that these dreams tend to be more emotionally intense than dreams from other stages. People describe feeling more joy, more fear, more sadness, more anger. The emotions are heightened, more vivid, more present. This might be because REM sleep is a time when the brain is particularly active in areas related to emotion, like the amygdala. It's as if the emotional centers of the brain are turned up during REM, and that amplification gets reflected in the dreams you have. The stories might be strange, but the feelings are very real. REM dreams can have quick scene changes like gentle jump cuts. If you've ever noticed that your dreams seem to skip around, jumping from one location to another without any transition, that's a common feature of REM dreams. You might be in your house one moment and at the beach the next without any sense of having travelled there. Or you might be talking to one person and then suddenly you're talking to someone else, without any explanation of how that happened. These jump cuts don't feel jarring in the dream. They feel natural, because the dreaming brain doesn't require the same kind of logical continuity that waking experience does. The emotional thread holds the dream together, not the logical sequence of events. Non-REM dreams can feel like quiet thinking or simple imagery. When you dream during non-REM sleep, the experience is often less cinematic. It might feel more like you're lying in bed thinking about something, rather than participating in a story. You might have a sense of pondering a problem, or a vague awareness of colours or shapes, or a feeling of presence without any specific visual details. These dreams are harder to describe because they're less structured, less narrative, but they're still a form of dreaming, and they can still carry emotion and meaning. They're just quieter, simpler, more abstract. Both kinds of dreams are real dreams, just different textures. There's sometimes a tendency to think of REM dreams as the real dreams, and non-REM dreams as something lesser, but that's not quite right. They're both genuine dream experiences. They're both your brain doing its nighttime work. They just have different qualities, different feels. REM dreams are like vivid movies. Non-REM dreams are like soft impressions or quiet thoughts or gentle drifting. Both are valid. Both are part of the full spectrum of what dreaming can be. REM sleep includes bursts of eye movement under the lids. This is where the name comes from. If you were to watch someone in REM sleep, you'd see their eyes moving rapidly back and forth beneath their closed eyelids. Scientists aren't entirely sure why this happens. One theory is that the eye movements correspond to visual imagery in the dream, as if the person is watching the dream unfold and their eyes are tracking the action. Another theory is that the eye movements are just a byproduct of the brain activity that characterizes REM sleep, not directly related to the dream content. Either way, those rapid eye movements are one of the most distinctive features of this sleep stage. In REM, the body's large muscles are largely offline to keep you safe. This is called rematonia, and it's a kind of temporary paralysis that affects most of your voluntary muscles. Your arms, your legs, your torso, they're all relaxed and essentially immobile during REM sleep. This is a protective mechanism. Because REM dreams can be so vivid and story-like, and because they often involve movement, your brain temporarily disconnects your muscles from motor commands. Otherwise, you might actually act out your dreams, which could be dangerous. You might thrash around or fall out of bed, or hurt yourself or someone sleeping next to you. The paralysis keeps you safe, keeping your body still while your mind runs wild. That temporary stillness is normal and protective. Sometimes people become aware of this paralysis as they're falling asleep or waking up, and it can be alarming if you don't know what it is. You might feel like you can't move, or like there's a weight on your chest, and for a moment it can feel frightening. But it's completely normal. It's just your brain's safety system doing its job. The paralysis only lasts for the duration of REM sleep, and then your muscles come back online. There's nothing wrong. It's just a brief moment where you're conscious of a process that usually happens without your awareness. Non-REM sleep supports deep physical restoration. While REM sleep is often associated with dreaming and mental processing, non-REM sleep is when a lot of the physical repair work happens. Your body releases growth hormone, your cells repair damage, your immune system strengthens, your brain clears out metabolic waste products that accumulated during the day. This deep restorative sleep is just as important as REM, even though it doesn't get as much attention. Both stages serve crucial functions. You need both to feel rested and healthy. Dreaming and restoration can overlap rather than compete. There's sometimes a misconception that dreaming takes away from the restorative quality of sleep, that it would be better to sleep without dreaming so your brain could rest more completely. But that's not how it works. Dreaming is part of the restorative process. The brain is doing important work when it dreams, work that contributes to memory, emotion regulation, creativity, and problem solving. Restoration doesn't mean shutting down. It means shifting into a different mode of activity, a mode that includes dreaming. You don't have to choose between dreaming and resting. They happen together. Some people report their calmest dreams in non-REM stages. While REM dreams get a lot of attention for being vivid and intense, some people find that their most peaceful, most soothing dream experiences happen during non-REM sleep. These are the dreams that feel like floating, or like being held in warmth, or like drifting through soft colours. They're not exciting or dramatic, they're just gentle and pleasant. For people who sometimes find their REM dreams too intense or emotionally charged, non-REM dreams can be a welcome respite, a quieter space within sleep. Just one more small fact, and then we drift. Dreams often amplify emotion because the brain is processing feelings quietly. One of the jobs dreams seem to do is help us work through emotional experiences. During the day, you might encounter something that makes you feel a certain way, but you're busy, you're focused on other things, you don't have time to fully process that emotion. At night, during sleep, the brain has the opportunity to return to those emotions and process them more thoroughly. And in dreams, those emotions can be amplified, exaggerated, played out in symbolic or metaphorical ways. It's as if the brain is saying, okay, now we have time to really feel this, to really explore what this means. The amplification isn't random, it's part of the processing. A small detail in a dream can trigger a big feeling. Dreams have a way of taking tiny, seemingly insignificant details and imbuing them with enormous emotional weight. You might dream about a particular object, a cup, a book, a piece of clothing, and in the dream, that object feels incredibly important, maybe even overwhelming. The emotion doesn't necessarily match the object in any logical way. A cup is just a cup. But in the dream, it might represent something else, something deeper, and the feeling is very real. This is part of how dream logic works. Emotion drives meaning, and even small symbols can carry large emotional loads. Dream emotions can be real even if the story is strange. This is important to understand. Just because a dream doesn't make logical sense doesn't mean the emotions in the dream aren't genuine. You might dream about something impossible, something absurd, something that could never happen in waking life. But if you feel fear in that dream, the fear is real. If you feel joy, the joy is real. The brain processes emotion the same way whether you're awake or asleep. The story might be fiction, but the feelings are authentic. This is one reason why nightmares can be so distressing, and why happy dreams can leave you feeling good all day. The emotions have real weight. Dreams can tag memories with emotion to help you learn from them. This is one of the theories about why we dream. The idea is that dreams help consolidate memories by attaching emotional significance to them. When something important happens during the day, the brain might replay that event in a dream, but with heightened emotion, to make sure the memory sticks. The emotion acts like a highlighter, marking the memory as significant. Later, when you encounter a similar situation, the emotional tag helps you respond appropriately. You remember not just what happened, but how it made you feel, and that combination of memory and emotion guides your future behavior. Stress can increase emotional intensity in dreams. When you're going through a stressful period in your life, your dreams often reflect that stress. They might be more intense, more anxiety-provoking, more filled with difficult emotions. This isn't the brain being cruel, it's the brain trying to process the stress, to work through it, to find some resolution or at least some way of holding it. Stress dreams can be unpleasant, but they're often part of the coping process. The brain is using the dream space to grapple with challenges that feel overwhelming during waking hours. It's doing emotional labor while you sleep. Calm days can lead to softer, more neutral dream tones. On the flip side, when your waking life is peaceful and relatively stress-free, your dreams often become gentler too. The emotional temperature drops. Dreams might be more pleasant, more neutral, less intense. You might have dreams that feel aimless and wandering, without much emotional charge at all. This is a sign that your brain doesn't have a lot of urgent emotional processing to do. It's just drifting, playing with images and ideas without any particular agenda. These can be some of the most restful dreams, the ones that let you sleep deeply without any disturbance. The same dream image can feel different in different moods. If you dream about the ocean, that dream might feel peaceful and calming one night, and frightening and overwhelming another night. The image is the same, but the emotional context changes everything. Your mood, your recent experiences, your current concerns, all of these influence how your brain interprets and responds to dream imagery. This is one reason why dream dictionaries, which try to assign fixed meanings to symbols, are so limited. The meaning of a dream symbol isn't fixed. It's personal, contextual, and fluid. The ocean doesn't mean one thing. It means whatever it feels like in that particular dream, in that particular moment of your life. Dreams often focus on social situations and belonging. When researchers analyze large collections of dream reports, they find that a huge percentage of dreams involve other people. Dreams about social interactions, relationships, conflicts, connections. This makes sense when you think about how important social life is to human beings. We're deeply social creatures, and a lot of our emotional energy goes into navigating relationships and maintaining our sense of belonging. Dreams reflect that preoccupation. They're often rehearsals or explorations of social dynamics, working through questions like, am I accepted? Am I safe? Do these people like me? How should I respond to this conflict? The brain is using dream time to process social information. Many dreams revolve around goals, challenges, or transitions. Another common theme in dreams is striving. You're trying to get somewhere, or accomplish something, or overcome an obstacle. You're late for something important, or you're searching for something you've lost, or you're facing a challenge that feels just beyond your ability. These dreams often reflect the goals and challenges in your waking life. If you're working towards something, if you're in a period of transition, if you're facing uncertainty, those themes show up in your dreams. The brain is exploring different possibilities, different outcomes, different ways of handling the situation. It's problem-solving in its own strange, symbolic way. Sometimes a dream is just the brain sorting feelings, nothing to interpret. Not every dream has to mean something. Not every dream is a message from your unconscious or a puzzle to be solved. Sometimes a dream is just your brain doing routine maintenance, sorting through emotions and memories, filing things away, clearing out clutter. It's like defragmenting a hard drive. The process is important, but the specific content that comes up during the process doesn't necessarily have deep significance. You can have a dream, wake up, and simply let it go without analyzing it. That's perfectly fine. The dream has already served its purpose just by happening. Just one more small fact, and then we drift. Dreams often pull from recent memories, called day residue. This is one of the most consistent findings in dream research. If you pay attention to your dreams, you'll often notice elements from the previous day showing up. A conversation you had, a place you visited, something you watched on TV, a problem you were thinking about. These fragments of recent experience get woven into the dream narrative. It's as if the brain is reviewing the day's events, deciding what to keep and what to discard, and in the process, those memories bubble up in dream form. Day residue doesn't usually show up exactly as it happened. It gets transformed, blended with other elements, but it's recognizable if you look for it. Dreams can also pull from older memories, called dream lag. Interestingly, dreams don't just draw on yesterday. There's a phenomenon where memories from about a week ago show up in dreams more often than you might expect. This dream lag effect suggests that the brain is doing multiple passes over recent memories, reviewing and consolidating them over several days. A memory might not appear in your dreams the night after it was formed, but it might show up a week later when the brain is doing a deeper level of processing. This is part of the complex multi-stage process of turning experience into long-term memory. The brain blends memories the way a painter blends colours. When you remember something while you're awake, you usually try to remember it accurately, exactly as it happened. But in dreams, the brain is much more free with memory. It takes pieces from different memories and blends them together, creating something new. You might dream about a conversation that combines elements from 3 different real conversations, or a place that's part your grandmother's house and part your elementary school. The brain isn't trying to be historically accurate, it's trying to create a meaningful experience, and sometimes meaning comes from combining things in unexpected ways. Your dream setting can be a mix of multiple places at once. This is one of those things that feels perfectly normal in a dream, but would be impossible in waking life. You might be in your kitchen, but it's also somehow your office, and also the house you grew up in. All 3 places exist simultaneously in the dream space. You don't question it, it just is. This blending of locations often reflects an emotional or thematic connection between those places. They're combined because they share some quality, some feeling, some significance in your life. The dream is using physical space to represent psychological space. A dream character can combine traits from different people you know. Just like places can blend, so can people. You might dream about someone who looks like your friend but acts like your sibling and has your co-worker's voice. Or you might dream about a person who seems to be one specific individual, but when you wake up and think about it, you realize they actually had characteristics from several different people. The brain creates composite characters, pulling traits from its library of faces and personalities. These blended characters often represent something broader than any one individual. They might represent a type of relationship, or a quality you associate with multiple people, or a role that different people have played in your life. The brain is especially good at stitching moments into a scene. One of the remarkable things about dreaming is how coherent dream scenes can feel, even though they're constructed from disparate elements. You might have fragments from different times, different places, different contexts, but in the dream, they all fit together into what feels like a unified experience. The brain is incredibly skilled at creating narrative coherence out of random pieces. It finds connections, builds bridges, makes it all feel like it belongs together. This is part of what makes dreams feel meaningful, even when they're logically nonsensical. The emotional and thematic coherence is strong enough that the logical gaps don't matter. Dreams can rehearse social scenarios in a low-stakes way. Some researchers think one function of dreaming is social simulation. In dreams, you can practice difficult conversations, explore different responses to social challenges, work through conflicts, all without any real-world consequences. If the interaction goes badly in the dream, nothing is actually lost. You can try again, or just let the dream move on to something else. This might be one way the brain prepares you for waking social interactions, giving you a kind of practice space where you can explore different possibilities. Dreams can remix skills you practice during the day. There's evidence that when you learn a new skill, your brain continues to work on it during sleep. You might dream about the skill directly, or you might dream about something that uses similar cognitive or physical patterns. Athletes sometimes dream about their sport. Musicians dream about playing instruments. Students dream about studying. These dreams seem to be part of the consolidation process, helping to strengthen the neural pathways associated with the skill. You're literally practicing in your sleep, even though you're not consciously trying to. Sleep supports memory consolidation, sorting what to keep. One of the most important functions of sleep is deciding which memories to strengthen and which to let fade. Not everything that happens during the day needs to be remembered forever. Some things are important, some things are trivial. During sleep, the brain reviews recent experiences and decides what's worth keeping. Dreams might be a side effect of this process, or they might play an active role in it. Either way, when you wake up after a good night's sleep, your memories are organized differently than they were when you went to bed. They're sorted, strengthened, integrated into your existing knowledge. Some dreams feel like the brain filing papers in a quiet office. This is a nice metaphor for what non-REM dreams sometimes feel like. They're not exciting or dramatic, they're just the brain going through its routines, putting things in order, making sure everything is where it should be. There's a kind of quiet productivity to these dreams. You might not remember them, and they might not feel significant, but they're part of the essential work of sleep. The brain is maintaining itself, organizing itself, preparing for the next day. It's the background hum of cognitive maintenance. Just one more small fact, and then we drift. Learning something new can influence dream content. When you're in the process of learning something, especially something complex or challenging, it often shows up in your dreams. You might dream about the subject matter directly, or you might dream about situations that involve similar patterns of thinking. The brain is integrating the new information, connecting it to what you already know, and dreams are part of that integration process. If you're learning a language, you might dream in that language. If you're learning to play chess, you might dream about moving pieces on a board. The content of your learning becomes part of the content of your dreams. New places can show up in dreams for days afterward. When you visit somewhere new, your brain is taking in a huge amount of information. New sights, new sounds, new spatial layouts. It takes time to process all of that. For several nights after visiting a new place, you might dream about it, or dream about places that incorporate elements of it. The brain is working to build a mental map of this new environment, to understand it, to file it away in long-term memory. The dreams are part of that mapping process. By the time the new place stops showing up in your dreams, it's been integrated into your mental geography. Big life changes often increase vivid dreaming. When you're going through a major transition, moving to a new city, starting a new job, ending a relationship, having a baby, Your dreams often become more intense and more memorable. This is because your brain is dealing with a lot of new information and a lot of emotion. There's more to process, more to sort through, more to make sense of. Dreams are one of the tools the brain uses to handle that increased cognitive and emotional load. The intensity of the dreams reflects the intensity of the life change. Stress can make dreams more intense, even without being scary. Stress doesn't always show up in dreams as nightmares. Sometimes it just makes dreams feel more vivid, more urgent, more emotionally charged. You might have dreams that are confusing or frustrating or exhausting, without being frightening. The stress gets translated into a kind of dream intensity, a feeling that there's a lot happening, a lot to keep track of, a lot of weight in the experience. Even if the dream isn't unpleasant, you might wake up feeling like you've been working hard all night, because in a sense you have. Your brain has been working hard to process the stress. Relaxation routines can soften dream tone over time. If you develop a habit of winding down before bed, reading, meditating, doing gentle stretches, listening to calm music, that can influence your dreams over time. The brain starts to associate bedtime with relaxation, and that association can carry over into sleep. Your dreams might become gentler, less agitated, more peaceful. It's not an instant transformation, but over weeks and months, a consistent relaxation routine can shift the overall tone of your dream life. You're training your brain to approach sleep with calm, and that calm seeps into the dreams themselves. Exercise can affect sleep depth, which can affect dream texture. Regular physical activity tends to improve sleep quality. It helps you fall asleep faster and spend more time in deep restorative sleep. But exercise can also influence dreaming. Some people find that they dream less vividly when they exercise regularly, possibly because they're spending more time in deep, non-REM sleep and less time in lighter REM sleep. Others find that exercise makes their dreams more pleasant. The relationship between exercise and dreams is individual and complex, but there's definitely a connection between how you use your body during the day and what your brain does at night. Alcohol can reduce REM earlier in the night and rebound later. Alcohol is a sedative, and it can help you fall asleep quickly. But it disrupts the normal architecture of sleep. Early in the night, alcohol suppresses REM sleep, so you spend less time dreaming. But as the alcohol wears off, there's often a REM rebound, where you suddenly enter very intense REM periods in the early morning hours. These rebound dreams can be especially vivid and sometimes disturbing. This is one reason why people who drink heavily often report having strange, intense dreams in the hours before they wake up. The alcohol has disrupted the normal rhythm, and the brain is trying to catch up on the REM sleep it missed earlier. Caffeine late in the day can reduce sleep quality and affect dreams. Caffeine is a stimulant, and it can stay in your system for hours. If you have coffee or tea or an energy drink late in the afternoon or evening, it can make it harder to fall asleep, reduce the amount of deep sleep you get, and make your sleep more fragmented. All of this can influence dreaming. You might have more wakeful periods during the night, which could increase dream recall because you're waking up more often. Or you might have more restless, agitated dreams because your brain is being stimulated by the caffeine even while you're trying to sleep. The relationship is complex, but the general principle is clear. What you put in your body affects how you sleep and how you dream. A consistent schedule helps the brain dream in steadier rhythms. One of the best things you can do for your sleep, and by extension your dreams, is to keep a consistent sleep schedule. Going to bed at roughly the same time each night and waking up at roughly the same time each morning helps regulate your circadian rhythm. When your circadian rhythm is stable, your sleep cycles become more predictable and more efficient. You spend the right amount of time in each stage of sleep. Your dreams tend to be more regular, less chaotic. Your brain knows what to expect and it can do its nighttime work more smoothly. Your dreams reflect your brain's inputs, not predictions or prophecies. This is worth stating clearly because there's a long, cultural history of treating dreams as messages from the divine, or glimpses of the future, or mystical revelations. But from a scientific perspective, dreams are simply the brain processing information it already has. They're made from your memories, your emotions, your experiences, your concerns. They can feel prophetic because they sometimes touch on themes that are relevant to your life, but they're not actually predicting the future. They're reflecting the present or processing the past. They're your brain talking to itself, not receiving messages from some external source. Just one more small fact, and then we drift. A lucid dream is when you realize you're dreaming while dreaming. It's a strange and fascinating state of consciousness. You're asleep, you're dreaming, but some part of your awareness knows that it's a dream. You might think, wait, this doesn't make sense. I must be dreaming. And then you are, in a sense, awake within the dream. You're still asleep. The dream is still happening. But you have a kind of meta-awareness, a recognition of the dream as a dream. This can happen spontaneously, or some people train themselves to do it more regularly. Either way, it's a unique experience that blurs the line between sleeping and waking consciousness. Lucid dreams are reported by many people, sometimes rarely, sometimes often. Most people have had at least one lucid dream at some point in their life, even if it was brief or fleeting. For some people, lucid dreams are very rare, happening maybe once or twice in a lifetime. For others, they happen more regularly, maybe once a month or even once a week. And a small number of people are naturally frequent lucid dreamers, experiencing lucidity in dreams most nights. The frequency varies widely from person to person, and it can change over the course of a lifetime. Someone who had lots of lucid dreams as a child might have them less often as an adult, or vice versa. Lucidity can be gentle, simply noticing, not controlling. There's a common misconception that lucid dreaming is all about control, about bending the dream to your will and making whatever you want happen. But lucidity doesn't have to be about control. It can be much gentler than that. You can simply notice that you're dreaming and then let the dream continue to unfold on its own. You're aware, but you're not interfering. You're watching with interest, curious about where the dream will go. This kind of gentle lucidity can actually be very pleasant and relaxing. There's less pressure, less effort, just a quiet awareness that adds an extra layer of interest to the dream. Trying too hard to control a dream can wake you up. One of the paradoxes of lucid dreaming is that the more you try to force things, the more likely you are to lose the dream entirely. If you become lucid and immediately start trying to change everything, the effort can be too much. Your brain gets too active, too engaged, and you wake up. The dream dissolves, and you're left lying in bed, fully awake, disappointed that the lucidity ended so quickly. The trick, if you want to maintain lucidity, is to stay calm, to make gentle changes rather than dramatic ones, to work with the dream rather than against it. Calm curiosity helps lucidity more than effort. The best mindset for lucid dreaming is a kind of relaxed exploration. If you realize you're dreaming, you can look around with interest, notice details, maybe try something small like flying a little bit or changing a color. But you stay calm, you stay curious, you don't strain. This calm curiosity keeps you in the dream longer and makes the experience more enjoyable. It's the difference between trying to force open a door and gently turning the handle. One approach creates resistance. The other works with the natural flow of things. Lucid dreams can be vivid, but they don't need to be productive. Sometimes people get interested in lucid dreaming because they want to use it for something. They want to solve problems or practice skills or have adventures or face fears. And you can do those things in lucid dreams. But you don't have to. A lucid dream can just be a pleasant experience, interesting for its own sake. You can enjoy the strangeness of being aware in a dream without needing it to serve a purpose. Not everything has to be productive. Sometimes it's enough just to notice, to be present, to appreciate the odd beauty of the dreaming mind. Some people use lucidity to soothe themselves inside a dream. This is one of the more therapeutic applications of lucid dreaming. If you're having an unpleasant dream, and you realize you're dreaming, you can sometimes shift the tone of the dream. You can remind yourself that it's not real, that you're safe. You can talk to dream characters who are frightening and ask them what they want. You can change the scenery or bring in a comforting presence. Some people find this incredibly helpful for dealing with recurring nightmares. The lucidity gives them a sense of agency within the dream, a way to reduce distress and feel more in control. Lucidity can fade in and out within the same dream. Lucid dreaming isn't usually a stable state. You might become lucid, stay aware for a few moments, and then lose that awareness and slip back into normal dreaming. Or you might drift in and out of lucidity multiple times within the same dream, gaining and losing awareness like a flickering light. This instability is normal. The brain is balancing between different states of consciousness, and sometimes you hover right at the edge between sleeping and waking awareness. It can feel frustrating if you're trying to maintain lucidity, but it's also part of the natural rhythm of how consciousness works during sleep. Not everyone wants lucid dreams, and that's perfectly fine. There's sometimes an assumption in discussions of lucid dreaming that it's something everyone should aspire to, that it's better than regular dreaming, but that's not true. Some people find lucid dreams interesting and enjoyable. Others find them exhausting or unsettling. Some people prefer to let dreams happen naturally, without any conscious interference. There's no right or wrong way to dream. If you're curious about lucidity, you can explore it. If you're not, you can simply let your dreams be what they are. Both approaches are valid. The most sleep-friendly approach is letting dreams do their own thing. From a purely restful sleep perspective, the best thing you can do is not worry too much about your dreams. Don't try to control them. Don't try to remember them if they don't want to be remembered. Don't analyze them to death. Just let them happen in the background while your body and brain restore themselves. Dreams will take care of themselves. They'll do whatever work they need to do. Your job is to sleep, to rest, to let the process unfold naturally. The more you can relax your grip on the whole experience, the more restful your sleep is likely to be. Just one more small fact, and then we drift. Recurring dreams are common, especially during stressful seasons. Most people have experienced at least one recurring dream, a dream that comes back again and again with the same basic theme or setting or situation. These dreams are especially common during times of stress or transition, when your brain is dealing with ongoing challenges or unresolved emotions. The dream repeats because the issue it's processing is still present, still active, still unresolved. Once the underlying stress is addressed, or the transition is complete, the recurring dream often stops on its own. Recurring dreams often revolve around unfinished feelings or patterns. The repetition is usually a sign that your brain is still working on something. There's an emotional pattern that hasn't been fully processed, or a problem that hasn't been solved, or a feeling that hasn't been fully felt. The dream keeps coming back because the work isn't done. This doesn't mean you need to consciously figure out what the dream means or solve the problem it represents. Often, just going through the process of living, of moving forward through your life, is enough. The brain will eventually finish its processing, and the dream will stop recurring naturally. Many people share common themes, like being unprepared or late. When researchers collect dream reports from large groups of people, they find certain themes that show up again and again across different individuals and cultures. Dreams about being late for something important. Dreams about being unprepared for a test or presentation. Dreams about being naked in public. Dreams about falling, or being chased, or losing teeth. These common themes seem to tap into universal human anxieties about competence, social acceptance, control, and vulnerability. The specific details vary from person to person, but the underlying emotional themes are remarkably consistent. These themes reflect emotion more than literal meaning. If you dream about being late for a test, that doesn't mean you're literally worried about an upcoming test. It means you're feeling some kind of performance anxiety, or fear of being judged, or concern about being unprepared for something. The test is a symbol, a way for your brain to represent a more general emotional state. The same goes for other common dream themes. Being chased doesn't mean you're literally running from someone. It means you're feeling pursued by something, maybe a fear or a responsibility or a feeling you're trying to avoid. The emotion is the core truth. The scenario is just the packaging. Dream symbols are personal. One person's ocean can mean calm, another's change. This is why dream dictionaries, which try to give universal meanings to symbols, are so limited. A symbol doesn't have one fixed meaning that applies to everyone. The meaning of a symbol depends on your personal history, your associations, your emotions. If you grew up near the ocean and have happy memories of beach vacations, the ocean in your dreams might represent peace and freedom. But if you had a frightening experience in the water, the ocean might represent danger or loss of control. The same symbol can mean completely different things to different people, or even to the same person at different times. The brain likes metaphors because they compress complicated feelings. Metaphors are efficient. They allow the brain to express something complex in a simple, condensed form. Instead of having a dream that explicitly works through all the nuances of a complicated relationship, you might dream about trying to pack a suitcase that won't close. The suitcase is a metaphor for the relationship, and the struggle to pack it represents the difficulty of managing all the complex feelings involved. Your brain doesn't have to spell it all out. The metaphor does the work, carrying all that emotional complexity in a single image. A dream can be about something without being a direct replay. Dreams rarely show you exactly what happened. They transform events, they shift perspectives, they blend different experiences together. So a dream about a specific challenge you're facing might not actually feature that challenge directly. It might represent the challenge through a completely different scenario that has the same emotional shape. You might dream about climbing a mountain when what you're really processing is a difficult project at work. The mountain and the project share a quality. They're both hard, they both require persistence, they both involve reaching a goal. The brain uses one to represent the other. You don't have to interpret a dream to benefit from sleep. This is important to remember. The benefits of sleep don't depend on you understanding your dreams or extracting meaning from them. Your brain is doing its work whether you remember the dreams or not, whether you interpret them or not. The processing happens automatically in the background. You can wake up feeling refreshed and restored without having any idea what you dreamed about. The dream did its job just by occurring. Your conscious engagement with it is optional. Sometimes a dream is just the mind wandering. Not every dream is profound. Not every dream is processing something important. Sometimes your brain is just idling, drifting from thought to thought and image to image without any particular purpose. It's like daydreaming, but asleep. Your mind wanders during the day, and it wanders at night too. These wandering dreams can be pleasant, or neutral, or even boring. They don't have to mean anything. They're just the brain doing what brains do, which is generate experience continuously, awake or asleep. A peaceful interpretation is allowed. My brain is processing and I'm safe. If you wake up from a dream and you're not sure what it meant, or if it seems strange or unsettling, you can always fall back on this interpretation. Your brain was doing its nighttime work and you're safe. You don't have to dig deeper if you don't want to. You don't have to find a hidden message. You can simply acknowledge that dreaming happened, that it's a normal part of sleep, and that you're okay. This kind of gentle, accepting attitude toward dreams often makes them less disruptive and helps you get back to sleep more easily if you wake during the night. Just one more small fact, and then we drift. Dreams are one way the brain explores possibilities without consequences. In waking life, every choice you make has real consequences. You have to commit to one path and let the others go. But in dreams, your brain can explore multiple possibilities simultaneously. It can play out different scenarios, try different approaches, see what happens without any real-world risk. This is part of how the brain prepares you for future challenges. It's running simulations, testing responses, building a repertoire of possibilities. When you wake up, you don't consciously remember most of this, but the learning is still there, encoded in your neural patterns. They can be creative because the brain loosens the usual rules. During waking hours, your brain operates under certain constraints: logic, physics, social conventions, the rules of language and narrative. These constraints help you function in the real world, but they also limit creativity. In dreams, many of these constraints are relaxed. Things can be impossible. Logic can be suspended. Conventions can be ignored. This loosening allows the brain to make connections it wouldn't make when fully awake, to combine ideas in novel ways, to see relationships that aren't obvious under normal constraints. Dreams can link distant ideas into surprising combinations. This is where some of the creative power of dreams comes from. Your brain can take two ideas that seem completely unrelated and put them together in a dream, and sometimes that combination reveals something interesting. Maybe it's a solution to a problem you've been working on. Maybe it's a new way of thinking about something. Maybe it's just a strange, beautiful image that sticks with you. The brain is exploring its own internal landscape, finding connections across distant territories of memory and thought. Some artists and scientists have reported inspiration from dreams. There are famous examples throughout history. Scientists who solved problems in dreams. Writers who got story ideas from dreams. Musicians who heard melodies in dreams and wrote them down when they woke up. Visual artists who saw images in dreams and later created them. Dreams can be a source of creative insight, though it's important not to romanticize this too much. Most dreams don't lead to breakthroughs. Most creative work happens through conscious effort, but occasionally, the free associative quality of dreaming can produce something genuinely useful or beautiful. But most dreams don't need a purpose, they can simply pass through, and This is the final important point about dreams. They don't all have to be meaningful. They don't all have to teach you something or show you something or give you something. Most dreams are just dreams. They happen, they fade, and that's okay. You can let them pass through without grasping at them, without needing them to be more than they are. They're part of the texture of sleep, part of the fabric of consciousness, and they don't require anything from you except the willingness to let them be. You're not required to remember your dreams to sleep well. Sleep quality and dream recall are separate things. You can have excellent restorative sleep and remember no dreams at all. You can have poor sleep and remember lots of dreams. The two aren't directly connected. What matters for your health and well-being is that you're getting enough sleep, that the sleep is relatively undisturbed, that you're cycling through the different stages properly. Whether you remember your dreams is interesting, but it's not essential. If you naturally remember dreams, that's fine. If you don't, that's also fine. Rest is still rest, even if the mind is making gentle images. Sometimes people worry that dreaming means they're not really resting, that their brain is too active, that they're working all night and not getting the restoration they need. But that's not how it works. The brain is supposed to be active during sleep. It's supposed to be dreaming, processing, organizing. That activity is part of rest, not opposed to it. Your brain rests in a different way than your body rests. It doesn't shut down, it shifts modes. And those shifts, including the shifts that produce dreams, are essential for health. If you wake from a dream, you can let it dissolve like fog. When you wake up in the middle of the night from a dream, you have a choice. You can try to hold on to it, analyze it, figure out what it means, or you can just notice it briefly and then let it go, let it dissolve like fog in the morning sun drifting away, becoming less and less distinct until it's gone completely. Often that second approach is more restful. You acknowledge the dream, maybe notice the general feeling it left behind, and then you relax back into sleep. The dream has already done whatever it needed to do. You don't need to work with it consciously. The next dream will come on its own, without effort. You don't have to make dreams happen. You don't have to try to dream. Dreams are spontaneous. They arise naturally from the sleeping brain. If one dream ends, another will come along eventually, without any effort on your part. You don't have to worry about whether you're dreaming enough, or dreaming the right kinds of dreams, or getting the most out of your dreams. They take care of themselves. Your role is passive. You simply sleep, and dreams appear and disappear like waves on a shore, each one arriving and receding according to its own rhythm. Tonight you can let dreams be quiet, poetry, arriving, fading, and leaving you deeper in sleep. This is perhaps the most restful way to think about dreams, not as problems to solve, or messages to decode, or experiences to control, but as quiet poetry, as images and feelings that drift through the night, beautiful or strange or mundane, but always temporary, always fading. They arrive without announcement, they leave without permission, and while they're there, they do their quiet work, whatever that work may be, and then they're gone, and you're deeper in sleep, deeper in rest, deeper in the gentle restoration that sleep provides. Just one more small fact, and then we drift. The images float farther away now, like lanterns on a dark lake, each one glowing softly for a moment before the distance makes it dim. You can watch them go without needing to follow. They were never meant to be held, only witnessed. The lake is wide and calm, and the lanterns drift according to currents you can't see and don't need to understand. This is the natural way of dreams. They come into view, they glow, they fade into the dark water of sleep. And you remain here, breathing slowly, jaw relaxed, nothing to do. There is nothing to chase anymore. No facts to remember, no concepts to grasp. The information has passed through, left its gentle mark and moved on. Your brain has heard what it needed to hear. It's sorting quietly now, filing, organizing, letting some things go and keeping others according to its own wisdom. You don't have to help. You don't have to solve anything. The work is happening below the surface, in the deep currents of sleep, and all you need to do is rest. Your breathing has its own rhythm now, steady and slow, in and out, without thought, without effort. Your body knows how to do this. It has been breathing all your life, and it will keep breathing through the night while you sleep. Each breath is an anchor, a gentle reminder that you are here, you are safe, you are exactly where you need to be. Nothing more is required of you. The night is long enough for all the dreams you need. You don't have to rush toward them or away from them. They will come in their own time, unfold in their own way, and leave when they're ready to leave. Some you'll remember, most you won't, and either way they will have served their purpose. Your brain will have done its nighttime work, and when morning comes, you'll wake restored, whether you remember the journey through the night or not. Let the last words fade now. Let them become as quiet as breath, as gentle as the space between thoughts. There is nothing left to say, nothing left to do, only sleep, deep and soft and welcoming. Only the night, holding you safely, only rest. The next story is about to begin. Please relax and enjoy. Sleep is an active biological process, not simply turning off. When you close your eyes at night and begin to drift away from waking consciousness, it might feel like you're powering down, like a machine being switched off at the end of a long day. But that's not quite what's happening. Your brain stays busy during sleep, just in different patterns. The networks that kept you alert and focused on the outside world begin to quiet, yes, but other networks wake up. Different systems take their turn at the front of the stage. Your sleeping brain is working, processing, organizing, maintaining. It's more like a theatre changing sets between acts than a theatre going dark. Sleep helps the body regulate many systems at once, like a nightly tune-up. While you're unaware of the world around you, your body's attending to 100 small tasks. Hormones are released on schedule. Tissues are inspected and repaired. Waste products are cleared away. Your immune system coordinates its efforts. Your metabolism recalibrates itself. All of this happens without your conscious involvement, like a city's maintenance crew working through the quiet hours when traffic has ceased. The work is essential, but it can only happen properly when the demands of daytime activity have paused. Humans are one of many species that sleep. Sleep is widespread in nature. From the smallest insects to the largest whales, creatures across the animal kingdom engage in something that looks like sleep. The details vary. Some animals sleep standing up. Some sleep with half their brain at a time, keeping the other half alert for danger. Some sleep for just a few hours, others sleep most of the day away. But the common thread is clear. Sleep is ancient, fundamental, woven into the fabric of life itself. It's not a modern invention or a cultural choice. It's biology, old as the nervous system itself. Most adults need a consistent amount of sleep, but the exact need varies. There's no single magic number that applies to everyone. Some people feel restored after 7 hours. Others need 8 or even 9 to feel truly rested. The variation is real and normal, shaped by genetics and individual biology. What matters more than hitting a specific number is consistency, getting roughly the same amount of sleep on a regular schedule. Your body learns what to expect. It prepares. It times its internal processes around that expectation. When you suddenly shift the schedule, the body has to adjust, and that adjustment takes time. Sleep tends to come in cycles rather than one long, flat state. When you fall asleep, you don't simply drop into one deep, unchanging pool of unconsciousness. Instead, you move through different stages, each with its own character and purpose. The sleep progresses in waves, cycles that repeat several times across the night. Each cycle lasts around 90 minutes, give or take, though the exact length can vary from person to person and night to night. As you move through these cycles, your brain shifts between different states, each serving a different function in the grand project of restoration and maintenance. You can be asleep and still respond to some sounds, especially familiar ones. The sleeping brain hasn't completely disconnected from the outside world. It's still monitoring, still listening at a low level. A mother can sleep through street noise but wake instantly to her baby's cry. You might sleep through a passing truck but startle awake at the sound of your own name. The brain is selective, filtering the environment even in sleep, deciding what matters and what can be ignored. It's a safety feature, an evolutionary inheritance from ancestors who needed to detect danger even while resting. Sleep is influenced by both biology and environment. Your genes set certain parameters, how much sleep you tend to need, whether you're naturally an early bird or a night owl, how deeply you sleep. But your environment also plays a powerful role: light and darkness, noise and silence, temperature and comfort, the cultural rhythms of your life, the demands of work and family, the habits you've built over years. All of these factors shape your sleep, sometimes working with your biology and sometimes working against it. Understanding both sides, the internal and the external, helps you see why sleep can feel so variable, so influenced by circumstances. The feeling of sleepiness is partly chemical and partly rhythmic. It's not one simple signal, but a conversation between different systems. Chemicals build up in your brain the longer you stay awake, creating a pressure that pushes you towards sleep. At the same time, your internal clock ticks along, marking the passage of hours, sending signals that say, "It's time," or "not yet." These two forces, the chemical pressure and the rhythmic timing, work together to create the sensation you recognize as sleepiness. When both are aligned, sleep comes easily. When they're out of sync, you might feel tired but unable to sleep, or wide awake when you think you should be tired. Resting quietly helps, but sleep has unique brain state features a rest can't fully replace. Lying down with your eyes closed is better than nothing. It lowers your heart rate, eases your muscles, gives your mind a break from constant input. But it's not the same as sleep. Sleep brings specific brainwave patterns that don't appear during quiet rest. It triggers the release of specific hormones. It activates cleanup and repair processes that only fully engage when you cross the threshold into actual sleep. Resting is valuable, especially when sleep won't come, but it doesn't substitute for the real thing. The brain knows the difference. Just one more small fact, and then we drift. Sleep is guided by sleep pressure, which builds the longer you stay awake. Imagine a weight that grows heavier with each passing hour of consciousness. When you first wake up in the morning, that weight is light, barely noticeable. You feel alert and clear. But as the day progresses, as you work and think and move through the world, the weight increases. By evening, it's substantial. By late night, it can feel almost overwhelming. This pressure is real, not metaphorical but chemical. Your brain is tracking how long you've been awake and adjusting your internal state accordingly. A key chemical linked to sleep pressure is adenosine, which accumulates during wakefulness. Adenosine is a byproduct of energy use. Every time your brain cells work, every time you think a thought, perceive a sensation, make a decision, they consume energy. That energy comes from breaking down ATP, a molecular fuel, and when ATP is broken down, adenosine is left behind. Throughout the day, adenosine levels rise. The longer you're awake, the more adenosine accumulates. This adenosine binds to receptors in your brain, and when enough receptors are occupied, they send a clear message: it's time to rest. The pressure you feel, that growing heaviness, is partly adenosine speaking. Sleep is also guided by the circadian rhythm, your body's internal daily clock. This clock runs on a roughly 24-hour cycle, ticking along whether you're awake or asleep, whether it's light or dark. It's controlled by a small cluster of neurons in your brain's hypothalamus, a region that serves as your body's timekeeper. This clock doesn't just tell you when to sleep, it coordinates countless processes across your body: when to release certain hormones, when to adjust your body temperature, when to prime your digestive system for food. It's a master conductor, keeping everything synchronized, ensuring that the right processes happen at the right time of day. Circadian rhythm helps determine when you prefer to sleep, not just how tired you are. You might have high sleep pressure, lots of adenosine accumulated, a heavy sense of fatigue, but if your circadian clock is signaling daytime, sleep can remain elusive. Your body is waiting for the right time, the time it's learned to expect. This is why jet lag feels so disorienting. Your adenosine levels might be sky high after a long flight, but your circadian clock is still tuned to your departure city's time zone. The two forces are pulling in different directions and your brain is caught in the middle, unsure whether it's supposed to sleep or wake. Light is the strongest external cue for circadian timing. Your circadian clock isn't psychic. It can't see the sun directly. Instead, it relies on information from your eyes. Special light-sensitive cells in your retina detect brightness and send signals to your brain's timekeeping center. Bright light, especially the blue-rich light of morning sun, sends a strong signal. It's daytime, time to be alert. Darkness sends the opposite signal. It's night, time to prepare for rest. Your brain uses these light cues to calibrate its internal clock, adjusting it slightly each day to stay aligned with the external world. Morning light tends to shift the clock earlier, evening light tends to shift it later. If you expose yourself to bright light early in the morning, your circadian clock interprets this as a signal that dawn has arrived, and it responds by advancing your internal schedule. You'll feel sleepy earlier that evening and wake up earlier the next morning. Conversely, if you expose yourself to bright light late at night, your clock interprets this as a signal that the day isn't over yet, and it delays your schedule. You'll feel alert later into the night and want to sleep in later the next morning. These shifts are gradual and subtle, but over time they can significantly change your sleep timing. Consistent timing helps the brain predict when to release sleep signals. Your brain loves predictability. When you go to bed at roughly the same time each night and wake at roughly the same time each morning, your brain learns the pattern. It begins to anticipate. It starts releasing sleep-promoting hormones like melatonin in advance of your usual bedtime. It prepares your body, lowering your core temperature, slowing your heart rate, shifting you into a state conducive to sleep. This preparation makes falling asleep easier. When your schedule is erratic, your brain can't predict, can't prepare, and sleep becomes more effortful. Sleep pressure and circadian rhythm work together, like two hands guiding the same door. Think of sleep as a door you pass through each night. One hand pushing that door is adrenaline, the chemical pressure that builds with wakefulness. The other hand is your circadian rhythm, the internal clock that says, now is the time. When both hands push together, when adenosine is high and your circadian clock is signaling night, the door swings open easily. Sleep comes naturally. But if only one hand is pushing, the door resists. High adenosine with the wrong circadian timing, or the right circadian timing without sufficient adenosine can leave you stuck in an uncomfortable middle ground. You can feel awake at night if circadian rhythm says day, even with high sleep pressure. This is the essence of insomnia for some people. They're exhausted. They've been awake for 16 or 18 hours. Adenosine has accumulated. But their circadian clock, for whatever reason, may be delayed by late-night light exposure, may be naturally inclined toward a later schedule, is still signaling alertness. Their brain is receiving mixed messages and alertness wins out. They lie in bed, tired but wired, unable to cross the threshold into sleep. It's frustrating because it feels like something should be simple but isn't. You can feel sleepy in the afternoon even if you slept well, because circadian rhythm dips. Most people experience a natural dip in alertness in the early to mid-afternoon, typically between 1 and 3 o'clock. This dip isn't caused by lunch, though eating can make it more noticeable. It's built into the circadian rhythm itself. Your internal clock has a small trough during this period, a brief downturn in alertness before it rises again into the evening. This is why siestas are culturally common in many parts of the world. The body is naturally inclined toward rest at this time. Even if your adenosine levels are low because you slept well the night before, the circadian dip can still make you feel drowsy. Just one more small fact, and then we drift. Sleep is commonly described in NREM and REM stages. These acronyms refer to two fundamentally different types of sleep. NREM stands for non-rapid eye movement sleep, and it's the more quiet, still form of sleep. REM stands for rapid eye movement sleep, named for the quick, darting motions your eyes make beneath your closed eyelids during this stage. These two types of sleep look different on a brain monitor, feel different if you happen to wake from them, and serve different functions for your body and mind. Together they make up the architecture of a night's sleep, alternating in a regular pattern. NREM sleep includes lighter and deeper phases. NREM isn't one uniform state. It's usually divided into 3 stages, though scientists sometimes use different classification systems. Stage 1 is the lightest, a transitional zone between wakefulness and true sleep. You can be easily woken from stage 1, and you might not even realize you were asleep. Stage 2 is deeper. Your brain waves slow down, and distinctive patterns called sleep, spindles, and K-complexes appear. These patterns are thought to help protect your sleep from being disturbed by outside noise. Stage 3 is the deepest phase of NREM, sometimes called slow-wave sleep because your brain produces long, slow, rolling waves of electrical activity. This is the sleep people usually mean when they talk about deep sleep. Deep NREM sleep is often linked with physical restoration and slow brain waves. During this stage, your body is at its most relaxed, your muscles are loose, your heart rate and breathing slow to their lowest points of the night. Growth hormone is released, supporting tissue repair and growth. This is the sleep that feels most restorative. If you wake from deep NREM, you'll likely feel groggy and disoriented as though you've been dragged up from a great depth. The slow brain waves that characterize this stage, delta waves, reflect a high degree of synchronization across the brain. Large groups of neurons are firing in unison, creating a powerful rhythmic signal that seems to support the brain's maintenance work. REM sleep is often linked with vivid dreaming and active brain patterns. If you were to look at a brain scan during REM sleep, it might remind you of a waking brain. There's a lot of activity, a lot of fast, irregular waves. Your brain is burning nearly as much energy as it does when you're awake. Your eyes move rapidly beneath your eyelids, scanning a dream landscape that only you can see. Your heart rate and breathing become more variable, less regular than in NREM. And yet, despite all this activity, your large muscles are essentially paralyzed. Your brain sends a signal down your spinal cord that temporarily disconnects most motor commands, preventing you from acting out your dreams. It's a strange state, an active mind in a still body. A full sleep cycle repeats multiple times across the night. Each cycle moves through the stages in sequence. Light NREM, deeper NREM, back to lighter NREM, and then into REM. The cycle then starts again. Most people complete 4 or 5 of these cycles in a full night's sleep, each one lasting about 90 minutes, though the length and composition of each cycle changes as the night progresses. The first cycle might have more deep NREM and less REM. The last cycle might have very little deep NREM and a long stretch of REM. Your brain is orchestrating these shifts, responding to internal needs that shift across the hours of sleep. Early night sleep tends to contain more deep NREM. In the first part of the night, your brain seems to prioritize the deepest, slowest stages of sleep. This is when those long delta waves dominate, when your body is most profoundly at rest. If you measure sleep pressure, the adenosine load you've built up during the day, it's highest at the start of the night. Deep NREM seems to be the brain's way of responding to that pressure, of discharging it. As the night progresses and sleep pressure decreases, the need for deep NREM diminishes. Later cycles contain less of it, or none at all. Later night sleep tends to contain more REM. As the night wears on, REM periods grow longer. In the first cycle, you might get only a few minutes of REM. By the final cycle, before you wake in the morning, you might spend 30 or even 40 minutes in REM. This shift might be related to circadian timing. Your body temperature is rising as morning approaches. Your brain is preparing to wake up. REM sleep, with its active brain patterns, might serve as a bridge between deep sleep and wakefulness, a gentler way to transition back to consciousness. The dreams you have in these long morning REM periods are often the ones you remember, simply because you're more likely to wake directly from them. These shifts are normal and part of a healthy architecture. The changing composition of sleep cycles across the night isn't a flaw or a problem. It's design. Your brain knows what it's doing. Early in the night, when sleep pressure is high and you're far from needing to wake, deep NREM dominates. Later, when morning approaches and your circadian clock is nudging you toward wakefulness, REM takes over. This pattern has been shaped by evolution, refined over millions of years to serve the needs of a sleeping brain and body. Trusting this pattern, rather than worrying about it, can make sleep feel less mysterious and more manageable. Brief awakenings between cycles are common and often not remembered. As your brain transitions from one cycle to the next, it sometimes surfaces briefly into something close to wakefulness. You might shift position, adjust your blanket, open your eyes for a moment. These awakenings are normal and healthy. They're not a sign of insomnia or broken sleep. In fact, they're so common that most people experience several of them each night without even knowing it. The key is that they're brief. If you don't engage with them, if you don't start thinking about your day or checking the time, you'll usually slip back into sleep within seconds. The awakening never registers in memory, and by morning you have no idea it happened. Waking up isn't always a sign of bad sleep. It can be part of cycling. This is worth repeating because so many people worry when they wake during the night. They interpret it as evidence that something's wrong, that their sleep is broken. But waking between cycles is expected. It's part of how sleep works. The problem arises when the waking leads to worry, and the worry leads to prolonged wakefulness. The awakening itself isn't the issue, it's what you do with it. If you can accept it as normal, stay calm and wait for the next cycle to pull you back under, then those brief moments of wakefulness become invisible, forgotten by morning. Just one more small fact, and then we drift. During sleep, the brain changes how it communicates across networks. When you're awake, Your brain operates like a busy highway system with constant traffic between different regions. Information flows quickly and widely. Sensory regions talk to decision-making regions. Memory centers coordinate with attention networks. The whole system is integrated, connected, working together to process the constant stream of input from the world around you. But during sleep, especially deep NREM sleep, this pattern changes. Communication becomes more local, more isolated. Different regions seem to retreat into themselves, processing internally rather than coordinating across long distances. The brain becomes less like a connected highway system and more like a collection of separate villages, each doing its own work. Some brain regions become quieter, others stay surprisingly active. The parts of your brain that handle sensory perception, vision, hearing, touch, tend to quiet down significantly during sleep. This makes sense. Your eyes are closed, the world is still, there's not much to process. But other regions remain active or even increase their activity. The hippocampus, a structure crucial for memory, shows bursts of activity during certain sleep stages. The prefrontal cortex, involved in complex thinking and emotional regulation, remains engaged in its own particular way. Sleep isn't a uniform shutdown. It's a selective reallocation of resources, some systems resting while others work. The brain continues monitoring the environment at a low level. Even in deep sleep, your brain hasn't completely closed the door to the outside world. It's still listening, still watching, just with the volume turned way down. This low-level monitoring is why you can sleep through a thunderstorm but wake to the quiet sound of your child calling your name. Your brain is filtering, constantly evaluating incoming sounds and deciding whether they're important enough to warrant waking up. This filtering happens automatically, below the level of conscious awareness. It's a survival mechanism, inherited from ancestors who needed to detect predators even while sleeping in caves or under open sky. Memory processing often continues during sleep, especially after learning. If you spend the day learning something new, a language, a skill, a list of facts, your brain doesn't stop working on that material just because you've gone to bed. During sleep, especially during specific stages like stage 2 NREM and REM, your brain replays those experiences. Neurons that fired together during learning fire together again during sleep, strengthening the connections between them. This replay happens faster than real time, compressed into brief bursts of activity. It's as though your brain is practicing, reviewing, rehearsing the day's lessons without your conscious involvement. Sleep can help stabilize new memories so they're easier to recall later. Think of a new memory as a fresh footpath in soft ground. If you walk that path once and then never return, it might disappear, overgrown or eroded. But if you walk it repeatedly, it becomes established, clear, permanent. Sleep provides that repetition. It takes the fragile, temporary memories formed during the day and converts them into something more durable. The neural connections are strengthened. The memory becomes integrated into your existing knowledge network. When you wake, you might find that something you struggled to remember the day before now comes to you easily. Sleep has done its work consolidating what was unstable into something reliable. Sleep also helps the brain decide what to keep and what to fade. You experience far more during a day than you could possibly remember. Most of it is irrelevant. Background details, routine actions, forgettable conversations. Your brain needs to be selective, to prioritize what matters and let the rest go. Sleep appears to play a role in this curation process. During sleep, the brain seems to tag certain memories as important and allow others to weaken. The exact mechanism isn't fully understood, but research suggests that replay during sleep doesn't affect all memories equally. The ones that get replayed most are the ones that survive. The ones that don't get attention begin to fade. By morning, your mental landscape has been cleaned up, cleared of clutter. Emotional experiences may be refiled during sleep in a calmer context. When something emotionally intense happens during the day, the memory is often stored with a strong emotional charge attached. The memory and the emotion are bound together. But during sleep, particularly during REM, the brain may reprocess these emotional memories in a different way. The emotional intensity can be dampened, separated somewhat from the factual content of the memory. You might wake up with the memory intact but feeling less raw about it. This process isn't about forgetting or denial. It's about integration, about taking something overwhelming and making it manageable, something you can live with rather than something that controls you. Dreaming can occur in multiple stages, not only REM. While the most vivid, narrative-driven dreams tend to happen during REM sleep, dreaming isn't exclusive to that stage. People woken from deep NREM sometimes report mental activity, thoughts, images, sensations. These NREM dreams are usually less story-like, less visual, more abstract. They might feel more like thinking than experiencing, but they're still a form of mental activity, a sign that the sleeping brain is never entirely quiet. Even in the deepest stages of sleep, something is happening in your mind, some kind of processing or simulation that continues outside of conscious awareness. The brain can blend old memories into new combinations during dreams. Dreams often feel nonsensical because they're not bound by the rules of waking logic or physical reality. Your brain is free to mix and match, to create impossible scenarios, to combine people and places that have no business being together. This blending might seem random, but it could serve a purpose. By forming new associations, by connecting disparate memories in novel ways, your brain might be exploring possibilities, testing out ideas, generating creative insights. The strangeness of dreams might be a feature, not a bug, a way of thinking outside the constraints of waking rationality. That blending may be part of how creativity and insight sometimes appear after sleep. There are countless stories of people solving problems in their dreams or waking up with sudden insights they couldn't reach through conscious effort. The composer Paul McCartney reportedly heard the melody for Yesterday in a dream. The chemist Auguste Kekule is said to have discovered the ring structure of benzene after dreaming of a snake biting its own tail. Whether or not these stories are literally true, they point to something real. Sleep seems to facilitate a different kind of thinking, a more associative, less inhibited form of mental exploration. When you wake, you sometimes bring those insights back with you, just one more small fact, and then we drift. Dreams can feel meaningful even when they're built from random fragments. You wake from a dream convinced it was trying to tell you something. The images felt symbolic. The emotions felt significant. The narrative, however strange, seemed to carry weight. This feeling of meaning is powerful and it's real, not in the sense that the dream is a message from your subconscious or a prophecy of the future, but in the sense that your brain is designed to find patterns and create meaning. Even if the dream was assembled from random neural firings and memory fragments, your waking mind will try to interpret it, to impose structure and significance on it. That's what minds do. They make sense of things. Many dreams include familiar places and faces because memory supplies easy material. Your brain doesn't create dreams from nothing. It draws on what's already stored in memory. People you know, places you've been, objects you've seen. These are the building blocks. It's easier and faster for your brain to pull up an existing image than to generate something entirely new. So your dreams are populated with the familiar even when the context is bizarre. You might be in your childhood home, but it has extra rooms you've never seen. You might be talking to a friend, but they say things that friend would never say. The elements are familiar. The combinations are novel. Dream time can feel stretched or compressed compared to clock time. A dream that feels like it lasted hours might have unfolded in just a few minutes of real time, or a brief dream moment, falling, turning around, might coincide with a long stretch of REM sleep. Time in dreams is subjective, disconnected from the steady ticking of the clock. Your brain isn't tracking real time while you're dreaming. It's constructing a narrative, and that narrative has its own internal pacing. When you wake and try to remember the dream, you might have trouble estimating how long it lasted. The dream's duration is difficult to map onto real time because the two operate on different scales. Not remembering dreams is common and normal. Some people wake every morning with vivid dream memories. Others rarely remember anything. This variation is normal and doesn't indicate anything wrong with your sleep or your brain. Dream recall depends on several factors, whether you wake during or immediately after REM sleep, whether you lie still and try to remember, whether you're in the habit of paying attention to dreams. If you don't remember your dreams, it doesn't mean you're not dreaming. You are. Everyone dreams multiple times each night. It's just that the memories aren't making it from the sleeping brain into the waking mind. They're dissolving in the transition. Dream recall can depend on when you wake within a sleep cycle. If you wake naturally at the end of a REM period, you're much more likely to remember the dream you were just having. The memory is fresh, recent, still active in your mind. But if you wake from deep NREM, or if you sleep through the end of a REM period and only wake later, The dream memory has already started to fade. It's like trying to remember something from hours ago versus trying to remember something from seconds ago. The timing makes a huge difference. This is why you might remember dreams on mornings when you wake naturally, but not on mornings when an alarm yanks you out of sleep at an arbitrary point in your cycle. Stress can change dream tone, but it doesn't mean anything is wrong with you. When you're stressed or anxious, your dreams often reflect that. They might be more intense, more negative, more focused on threats or problems. This is your brain processing the emotional content of your waking life. It's not pathological. It's not a sign that you're failing to cope. It's just your mind doing what it's designed to do, working through experiences, including difficult ones. When the stress passes, the dreams usually shift back to their typical tone. The content of your dreams can be a mirror of your emotional state, but it's not a fixed or permanent reflection. It changes as you change. The brain often uses metaphors because it thinks in patterns, not sentences. Dreams are rarely literal. They deal in symbols, associations, feelings. Your brain doesn't have access to language in the same way while you're dreaming, so it communicates through images and scenarios. Being chased might represent a feeling of pressure or avoidance in your waking life. Flying might represent freedom or escape. But these interpretations are personal and contextual, not universal. The same dream image might mean different things to different people, or even different things to the same person at different times. The brain is pattern matching, linking current concerns to past experiences, creating a visual emotional shorthand that feels meaningful even when it's not immediately clear. Some dreams are more narrative, others are more like sensations or moods. Not all dreams unfold as stories. Some are just impressions, a colour, a feeling, a sense of presence. You might wake with a strong emotion but no clear memory of what happened in the dream to create that emotion. Or you might remember a single image, vivid and isolated without any context or storyline around it. These fragmentary dreams are just as real as the more elaborate ones, they're just different. Forms of the same underlying process, your brain active during sleep, generating experience even in the absence of external input. Night thoughts can feel louder because daytime noise and tasks are gone. When you lie down at night and close your eyes, the world becomes quiet. All the distractions that kept your mind occupied during the day are suddenly absent. In that quiet, your thoughts can seem amplified. Worries you barely noticed during the day can suddenly feel urgent. Small problems can feel large. This isn't because the thoughts or problems have changed. It's because your attention is no longer divided. You're focused inward, and everything internal feels more prominent. This can make falling asleep difficult, especially if the thoughts are anxious or uncomfortable. A quiet mind sometimes surfaces open loops simply because it finally has space. During the day, you're juggling tasks, responding to demands, moving from one thing to the next. Your mind doesn't have time to stop and review. But at night, in the stillness before sleep, those unresolved tasks and unfinished thoughts come forward. Your brain is essentially saying, "Hey, remember this? We didn't finish this." It's not trying to torment you. It's just doing its job, keeping track of what needs attention. The problem is that bedtime isn't the right time to address those things. Acknowledging them without engaging can help. You can tell yourself, "Yes, I see you. I'll handle you tomorrow," and then gently redirect your attention back toward rest. Just one more small fact, and then we drift. While you sleep, your breathing patterns often change and slow. When you're awake, your breathing is somewhat irregular, influenced by activity, emotion, and conscious thought. You might take a deep breath before speaking, or breathe faster when you're anxious. But as you fall asleep, that conscious control fades. Your breathing becomes automatic, governed by brainstem regions that operate below conscious awareness. The rhythm often slows and becomes more regular. Each breath deepens slightly. The pauses between breaths may lengthen. This slower, steadier breathing is part of the body's shift into rest mode, a signal that the nervous system is standing down from its daytime vigilance. Heart rate often drops during deeper stages, though patterns vary. Just as your breathing slows, your heart rate typically decreases during sleep. When you're awake and active, your heart might beat 70 or 80 or 90 times per minute, depending on what you're doing. As you move into deeper sleep, that rate can drop significantly, perhaps down to 50 or 60 beats per minute, sometimes even lower. This reduction makes sense. Your body isn't moving. It doesn't need as much oxygen delivered to muscles. The cardiovascular system can ease off, conserving energy while still maintaining essential functions. During REM sleep, the pattern becomes more variable again, with heart rate fluctuating in response to dream content and the increased brain activity of that stage. Body temperature tends to drift downward at night as part of circadian rhythm. Your core body temperature isn't constant throughout the day. It follows a circadian pattern, rising during the daytime and falling at night. The nighttime drop is significant, sometimes a full degree or more. This cooling is tightly linked to sleep. In fact, the drop in core temperature seems to be a signal that helps initiate sleep. Your body begins cooling a few hours before your usual bedtime, preparing for rest. If that cooling is disrupted, if you're too hot, or if you exercise intensely close to bedtime, falling asleep becomes harder. The body is waiting for the temperature signal that says it's time to sleep, and that signal hasn't arrived. Your muscles relax more deeply in certain stages. When you're awake, your muscles maintain a baseline level of tension, ready to move at a moment's notice. As you enter lighter stages of sleep, that tension begins to ease. You might shift position, settle into a more comfortable posture. But during deep NREM sleep, your muscles relax even further. They become loose, heavy, nearly limp. This deep relaxation allows the body to rest completely, to release the accumulated tension of the day. The relaxation isn't complete paralysis. You can still move if needed, but it's a profound letting go, a surrender of the body's readiness to act. During REM, the body reduces most large muscle movement, a normal protective feature. While your brain is active during REM, creating vivid dreams full of action and emotion, your body is still. This stillness is deliberate, controlled by a mechanism in the brainstem that temporarily blocks motor commands from reaching your muscles. It's called REM-atonia, and it serves an important purpose. It prevents you from acting out your dreams. Without this protective paralysis, you might thrash around, throw punches, run in place, physically, enacting whatever your dreaming mind is experiencing. Some people have a condition where this mechanism doesn't work properly, and they do act out their dreams, sometimes injuring themselves or their bed partners. But for most people, REM-atonia works perfectly, keeping the body safe while the mind wanders. Your immune system uses sleep as a time to coordinate and reset activity. While you're awake, your immune system is busy responding to the constant challenges of daily life: bacteria, viruses, allergens, minor injuries. But sleep provides an opportunity for a different kind of work. During sleep, certain immune cells become more active. Signaling molecules are released that help coordinate immune responses. The body seems to use this time to repair damage, clear out pathogens, and prepare for the next day. This is one reason why sleep loss makes you more vulnerable to illness. When you don't sleep enough, your immune system doesn't get the downtime it needs to maintain itself. Growth and repair processes are more active during sleep, especially in youth. In children and adolescents, sleep is when growth hormone is released in its largest quantities. This hormone promotes physical growth, helping bones lengthen and muscles develop. Even in adults who aren't actively growing, sleep remains a time for repair. Tissues damaged during the day are mended, skin cells regenerate, muscle fibers rebuild. The body is essentially performing maintenance, fixing the small wear and tear that accumulates from living. This work can happen during waking rest to some extent, but it reaches its peak during sleep when the body's resources aren't diverted to other tasks. Sleep helps regulate appetite-related hormones. Two key hormones involved in hunger and satiety, ghrelin and leptin, are influenced by sleep. Ghrelin signals hunger, leptin signals fullness. When you sleep well, these hormones stay in balance, but when you're sleep deprived, the balance shifts. Ghrelin levels rise, making you feel hungrier. Leptin levels fall, making it harder to feel satisfied after eating. This hormonal shift helps explain why sleep-deprived people often find themselves craving high-calorie foods and eating more than usual. It's not a lack of willpower, it's biology. Your body is trying to compensate for the missing sleep by seeking energy from food. That's one reason sleep loss can make cravings feel louder. Beyond the hormonal changes, there are also changes in brain activity related to sleep deprivation. The prefrontal cortex, the part of your brain involved in decision-making and impulse control, doesn't function as well when you're tired. At the same time, reward centers in the brain become more reactive to food, especially sweet and fatty foods, so you're simultaneously less able to resist cravings and more drawn to indulgent foods. It's a challenging combination. The cravings aren't imaginary or a personal failing. They're a predictable result of insufficient sleep. Sleep helps balance stress systems so the next day feels more manageable. Your body's stress response, the system that releases cortisol and adrenaline when you're under pressure, needs regular resetting. Sleep provides that reset. During sleep, cortisol levels drop, giving your system a chance to recover from the day's demands. When you wake after a good night's sleep, your stress system is recalibrated, ready to respond appropriately to new challenges. But when sleep is inadequate, cortisol can remain elevated, or the system can become dysregulated, overreacting to minor stresses. This is why everything feels harder when you're tired. Small annoyances become major frustrations. Manageable challenges feel overwhelming. Sleep deprivation doesn't just make you tired, it changes your emotional resilience. Just one more small fact, and then we drift. The brain's fluid system changes during sleep in ways linked to clearing waste products. Your brain is metabolically active, constantly burning energy and producing waste. During the day, these waste products accumulate. They need to be cleared away, but the brain doesn't have a traditional lymphatic system like the rest of your body. Instead, it has something called the glymphatic system, a network of channels that allows cerebrospinal fluid to flow through brain tissue, washing away metabolic waste. This system is most active during sleep, particularly during deep NREM sleep. The cells in your brain actually shrink slightly, widening the spaces between them and allowing fluid to flow more freely. It's a nightly cleaning cycle, essential for maintaining brain health. This cleanup idea is one reason sleep is considered essential maintenance. Just as a house accumulates dust and clutter and needs regular cleaning to remain livable, your brain accumulates metabolic byproducts and needs regular sleep to stay healthy. One of the waste products cleared during sleep is beta amyloid, a protein that can form plaques associated with Alzheimer's disease. Without adequate sleep, these waste products build up. Over time, that build-up may contribute to cognitive decline. This isn't meant to sound alarming. Sleep isn't the only factor in brain health, but it highlights why sleep isn't optional. It's not just about feeling rested, it's about basic biological maintenance. Sleep supports healthy communication between brain cells over the long term. Neurons communicate via synapses, tiny junctions where signals pass from one cell to another. These synapses aren't static, they're constantly changing, strengthening or weakening based on use. During waking hours, you're learning, experiencing, forming memories. New synapses are created, existing ones are strengthened. But this growth can't continue indefinitely. There has to be some pruning, some downscaling, or the system would become overloaded. Sleep appears to provide that balance. During sleep, synapses that aren't important are weakened, while important ones are preserved or even strengthened. It's a kind of neural housekeeping that keeps the system efficient and responsive. Deep sleep is often associated with the strongest slow-wave patterns. When researchers record brain activity during deep NREM sleep, they see large, slow oscillations, waves of electrical activity that sweep across the brain in synchronized rhythms. These slow waves are distinctive, easy to recognize, and they're associated with many of the benefits of deep sleep. The waves reflect coordinated activity across millions of neurons, all firing and resting in unison. This synchronization may be crucial for the brain's maintenance processes. It's as though the brain needs to quiet its normal, busy activity, all the independent chatter of different regions, in order to perform large-scale, system-wide tasks. Those slow waves may help coordinate widespread reset signals. Think of the slow waves like a conductor's baton moving through an orchestra. Each section of the orchestra, the strings, the brass, the woodwinds, follows the baton, playing together in time. Similarly, the slow waves during deep sleep may help coordinate activity across different brain regions, ensuring that maintenance processes happen in sync. Memory consolidation, synaptic pruning, waste clearance. All of these may be orchestrated by the slow wave activity, guided by those large, rolling oscillations that define deep NREM sleep. Sleep is also linked to stabilizing learning, especially skills and patterns. If you practice a new skill, playing a musical instrument, shooting a basketball, typing without looking, you'll improve during practice, but you'll improve even more after a night of sleep. This consolidation of motor skills is well documented. The neural circuits involved in the skill are replayed and refined during sleep, particularly during stage 2 NREM, where sleep spindles, brief bursts of rapid brain activity, seem to play a key role when you Wake. The skill feels smoother, more automatic. Your brain has been practicing while you slept. A nap can sometimes improve performance on certain tasks. Even a short nap, 20 or 30 minutes, can provide benefits, especially for tasks that require sustained attention or memory recall. A nap allows your brain to clear some accumulated adenosine, reducing sleep pressure temporarily. It can also provide a brief period of memory consolidation, helping to stabilize information you learned earlier in the day. Naps don't replace nighttime sleep, and napping too long or too late in the day can interfere with nighttime sleep, but a well-timed short nap can be restorative, a way to recharge midday. Short sleep loss can feel like mental fog because attention networks tire quickly. Even a single night of inadequate sleep can impair your ability to focus. Your attention becomes less stable, more prone to wandering. You might read the same sentence 3 times without absorbing it. You might lose track of what someone is saying mid-conversation. This isn't a failure of willpower, it's a biological consequence of sleep deprivation. The brain regions that support sustained attention, particularly the prefrontal cortex, are highly sensitive to sleep loss. They need rest to function optimally, and when they don't get it, performance suffers. Sleep can affect reaction time even when you feel fine. One of the insidious things about sleep deprivation is that you often don't realize how impaired you are. You might feel okay, alert enough to get by, but objective measures, tests of reaction time, decision-making, coordination, tell a different story. Your reactions are slower, your judgment is less reliable. This is particularly dangerous when driving or operating machinery. You think you're fine, but your brain is operating at reduced capacity. It's similar to being slightly intoxicated, except there's no obvious external sign. You can't smell sleep deprivation. The body often notices sleep debt before the mind admits it. Your body keeps track of how much sleep you're getting and how much you need. When there's a mismatch, when you're consistently sleeping less than your body requires, you accumulate sleep debt. Your body responds with fatigue, slower healing, increased vulnerability to illness, changes in appetite. These are signals, alarms telling you that something needs to change. But the mind can be stubborn. It might rationalize, insisting that you're fine, that you can push through. But the body doesn't lie. It knows what it needs. Just one more small fact, and then we drift. The brain treats light as information about time. Light isn't just something that helps you see. For your brain, light is a signal, a message about where you are in the day-night cycle. When light enters your eyes, it doesn't only go to the visual cortex where images are processed. Some of the signal branches off to your circadian clock, informing it about the external light environment. Bright light tells your brain it's daytime. Darkness tells it night has arrived. This system evolved over millions of years, when the only light sources were the sun, moon, and fire. Your brain still operates on those ancient assumptions. Bright screens can mimic day cues if used late at night. Modern technology has introduced a complication. Screens, phones, computers, tablets, televisions emit bright light, often rich in blue wavelengths that are particularly effective at signaling daytime to your brain. When you use these devices late at night, you're essentially telling your circadian clock that the day isn't over yet. Your clock responds by delaying the release of melatonin, a hormone that promotes sleepiness. It shifts your internal schedule later. You feel alert when you should be winding down. This doesn't mean screens are evil or that you must avoid them entirely, but it does mean timing matters. Using screens earlier in the evening has less impact than using them right before bed. Dim, warm environments tend to feel more night-like to the nervous system. Your brain is looking for cues that night has arrived, and one of those cues is a shift in light quality. Natural evening light is dimmer and warmer, more red and orange, less blue as the sun sets. Mimicking this transition in your home can help signal to your brain that it's time to prepare for sleep. Dimming lights in the evening, using warmer bulbs, avoiding harsh overhead lighting, all of these create an environment that feels more conducive to rest. It's not that dim light causes sleep directly. It's that it removes a signal that promotes wakefulness. A consistent wind-down routine can become a conditioned signal for sleepiness. Just as light is a signal for your circadian clock, your behaviors can become signals for your brain. If you do the same things every night before bed, perhaps you read for a few minutes, brush your teeth, put on comfortable clothes, your brain learns to associate those actions with sleep. They become part of a sequence, a ritual that ends in bed. Over time, simply starting the routine can trigger the early stages of sleepiness. Your brain anticipates what's coming. It begins the process of winding down before you've even turned off the lights. This conditioning is powerful and takes advantage of your brain's love of patterns. The brain loves patterns. Repeating bedtime cues can make sleep feel easier. Consistency signals safety to your nervous system. When things are predictable, your brain can relax. It doesn't need to stay alert for surprises. This is part of why a regular sleep schedule helps. Your brain knows what to expect. It prepares in advance. The same principle applies to your bedtime routine. The more consistent you are, going to bed at roughly the same time, following the same sequence of actions, the more your brain can automate the transition into sleep. It becomes less effortful, more natural. Sleep stops being something you have to force and becomes something that arrives on its own. Caffeine works mainly by blocking adenosine receptors, masking sleep pressure. Remember adenosine, the molecule that accumulates during wakefulness and creates sleep pressure. Caffeine is shaped similarly enough to adenosine that it can fit into the same receptors. When caffeine occupies those receptors, adenosine can't bind to them. The signal that says you're tired is blocked. But the adenosine is still there, still accumulating. Caffeine doesn't reduce sleep pressure, it just hides it. When the caffeine eventually wears off, all that accumulated adenosine floods the available receptors at once. This is why you sometimes feel a sudden crash after the effects of caffeine fade. The sleep pressure was there all along, masked by the drug. Caffeine's effects can linger longer than people expect, depending on the person. Caffeine has a half-life of about 5 or 6 hours in most people, though this varies based on genetics, age, and other factors. Half-life means that after 5 or 6 hours, half of the caffeine you consumed is still in your system. If you drink coffee at 3 in the afternoon, a quarter of that caffeine might still be active at bedtime. For some people, especially those who metabolize caffeine slowly, the effects last even longer. You might not feel wired, but the caffeine is still there, still blocking adenosine receptors, still making it harder to fall asleep. Being aware of this can help you time your caffeine intake more strategically. Alcohol can make people sleepy at first, but often disrupts later sleep structure. A drink or two in the evening can make you feel relaxed, drowsy, ready for bed. Alcohol is a sedative, and it does help some people fall asleep faster. But sleep after drinking alcohol is different from natural sleep. Alcohol suppresses REM sleep, particularly in the first half of the night. It can also increase the likelihood of waking in the second half of the night as your body metabolizes the alcohol. You might fall asleep easily, but wake up a few hours later, alert and unable to get back to sleep. The overall architecture of sleep is disrupted. You might spend enough time in bed, but the quality of that sleep is reduced. A cool room often feels more sleep-friendly because the body cools naturally at night. Remember that your core temperature drops as part of your circadian rhythm, signaling that it's time for sleep. A cooler environment facilitates that drop. It helps your body release heat, making it easier to reach the lower temperature that sleep requires. If your room is too warm, your body has to work harder to cool down. That effort can interfere with falling asleep or maintaining sleep. The ideal temperature varies from person to person, but most people sleep better in a room that's on the cooler side. Somewhere between 60 and 67 degrees Fahrenheit is often cited as optimal. Many people sleep best when the environment becomes predictably quiet and dim. Your brain is always scanning the environment for potential threats, even during sleep. Noise and light can both signal that something might need attention. A quiet, dim environment removes those signals. It tells your brain that everything is safe, that there's no reason to stay alert. This doesn't mean absolute silence and total darkness are necessary. Many people sleep fine with some ambient noise, a fan, white noise, distant traffic. The key is that the noise is consistent and predictable. It's sudden changes, a door slamming, a dog barking, a bright light flicking on, that startle the brain and interrupt sleep. Just one more small fact. And then we drift. Yawning is common and doesn't always mean boredom. It can relate to state changes. You yawn when you're tired, yes, but you also yawn when you first wake up, when you're about to do something stressful or sometimes for no clear reason at all. The exact purpose of yawning isn't fully understood, but it seems to be linked to transitions, shifts in your level of arousal or attention. Some researchers think yawning helps cool the brain, bringing in cooler air and increasing blood flow. Others think it's a way to stretch the muscles in your face and throat, or to increase oxygen intake. Whatever the mechanism, yawning appears to be a signal that your brain is changing gears, moving from one state to another. People can yawn more when they're tired because the brain is shifting gears. When you're fighting to stay awake, your brain is trying to maintain alertness despite high sleep pressure. Yawning might be part of that struggle, a reflexive attempt to increase arousal and ward off sleepiness. It's not particularly effective. Yawning won't replace sleep, but it's a sign that your brain is aware of the conflict between its current state and the state it needs to be in. Noticing that you're yawning frequently can be a useful signal to listen to. Your body is telling you it needs rest. Snoring is common and varies widely between people and nights. Snoring happens when the flow of air through your mouth and nose is partially blocked during sleep. The tissues in your throat relax, narrowing the airway, and as air moves through the narrowed space, it causes the surrounding tissues to vibrate. The result is the sound of snoring. Some people snore every night, others snore only occasionally, depending on factors like sleep position, nasal congestion, alcohol consumption, or fatigue. Snoring is common. Nearly half of all adults snore at least occasionally, and while it can be disruptive to bed partners, mild snoring is usually harmless. Loud, frequent snoring accompanied by pauses in breathing can be a sign of sleep apnea, a condition worth discussing with a doctor, but occasional snoring is generally just a normal variation in how sleep happens. Sleep talking can happen without the person remembering it. Also called somniloquy, sleep talking can occur during any stage of sleep, though it's most common during lighter stages and during transitions between stages. The person might mumble, speak clearly, or even seem to be having a conversation. Usually, what they say is nonsensical or fragmented, though occasionally it's more coherent. Sleep talking is generally harmless. It's not a sign of a sleep disorder or a psychological problem, and most people who talk in their sleep have no memory of it in the morning. It's your brain briefly activating speech centers while you're still asleep, a minor glitch in the system's usual boundaries between waking and sleeping. Sleepwalking is more common in children and often decreases with age. Sleepwalking or somnambulism tends to occur during deep NREM sleep, usually in the first third of the night. The person's brain is partially awake, enough to control movement and navigate the environment, but not fully conscious. They might walk around, open doors, or even perform routine tasks, all with their eyes open but a blank expression on their face. Sleepwalking is most common in childhood, and many children who sleepwalk will outgrow it by adolescence. In adults, sleepwalking can be triggered by stress, sleep deprivation, or certain medications. It's usually harmless, though safety is a concern because the person isn't fully aware of their surroundings. Hypnic jerks, little falling sensations, can happen as the body relaxes into sleep. Just as you're drifting off, you suddenly jolt awake, feeling as though you've tripped or fallen. This is called a hypnic jerk, or a sleep start, and it's completely normal. It happens during the transition from wakefulness to sleep, when your muscles are relaxing. One theory is that the brain misinterprets this relaxation as falling and sends a signal to the muscles to catch yourself. Another theory is that it's a leftover reflex from our evolutionary past, a way for tree-dwelling ancestors to wake themselves if they started to fall out of a tree while sleeping. Whatever the cause, hypnic jerks are common, harmless, and nothing to worry about. That sensation is a normal transition phenomenon for many people. The hypnic jerk can feel startling, even embarrassing if you're falling asleep in a public place. But it's not a sign of a sleep disorder or a neurological problem. It's just your nervous system navigating the border between waking and sleeping, and sometimes that navigation is a little clumsy. If hypnic jerks are frequent or severe enough to disrupt your sleep regularly, it might be worth evaluating factors like stress, caffeine intake, or sleep deprivation, all of which can make them more common. But for most people, they're just an occasional harmless quirk of falling asleep. Sleep paralysis can occur during transitions in or out of REM and can feel strange but is a known phenomenon. Sleep paralysis happens when you become conscious while your body is still in the paralyzed state of REM sleep. You're awake, aware of your surroundings, but you can't move or speak. It can last from a few seconds to a few minutes, and it can be accompanied by a feeling of pressure on your chest, difficulty breathing, or even vivid hallucinations, a sense of a presence in the room, shadowy figures, strange sounds. It feels frightening, but it's not dangerous. It's a mismatch in timing. Your mind has woken up before the signal to restore muscle control has been sent. Once your brain fully transitions to waking, the paralysis lifts and you can move again. Nighttime awakenings are common and often brief. Most people wake up several times each night, though they often don't remember it. These awakenings are part of the normal cycle of sleep, happening as you transition between sleep stages or between sleep cycles. They're usually very short, a few seconds, maybe a minute, and if you don't engage with them, if you don't start thinking or worrying or checking the clock, you'll fall back asleep quickly. The awakening doesn't register in memory, and by morning you have the impression that you slept straight through. It's only when the awakenings become longer or more frequent, or when they're accompanied by worry or frustration, that they become a problem. The ability to fall back asleep is often influenced by how alert the mind becomes during waking moments. If you wake in the night and immediately start thinking, replaying the day's events, planning tomorrow, worrying about the fact that you're awake, you activate your brain. You shift from a sleepy, drowsy state to a more alert, engaged state. Once that happens, falling back asleep becomes harder. But if you can stay calm, keep your mind quiet, resist the urge to engage with thoughts or check the time, your brain will often drift back into sleep on its own. The awakening was just a pause, a brief surfacing. It doesn't have to turn into prolonged wakefulness unless you let it. Just one more small fact, and then we drift. Sleep is older than modern life. It's built into biology, not willpower. Sleep existed long before electric lights, before cities, before agriculture. It existed before humans. It's a fundamental biological process, shaped by millions of years of evolution, essential to the survival of countless species. You don't have to earn sleep. You don't have to be perfect to deserve it. It's not a reward for productivity or good behavior. It's a need, as basic as eating or breathing. Your body is designed to sleep, and it will keep trying night after night, regardless of what your conscious mind thinks about it. You don't force sleep. You allow the conditions where sleep arrives. This is a subtle but important distinction. Sleep isn't something you can make happen through sheer effort. Trying harder to sleep usually backfires, creating tension and frustration that makes sleep even more elusive. Instead, your role is to create the right conditions, reducing sleep pressure during the day by getting enough light and activity, aligning your schedule with your circadian rhythm, creating a calm and comfortable environment, letting go of worry and effort at bedtime, and then allowing sleep to come when it's ready. Sleep is something that happens to you, not something you do. You can invite it, but you can't command it. Even imperfect sleep still provides some restoration. It's easy to focus on what went wrong. You didn't fall asleep as quickly as you wanted, you woke up in the middle of the night, you feel like you didn't sleep enough. But even on difficult nights, your body is still getting some rest, still completing some of its essential maintenance work. Even light sleep provides some benefit. Even fragmented sleep is better than no sleep. It's not ideal, and chronic poor sleep is a problem that deserves attention, but a single imperfect night isn't a disaster. Your body is resilient. It will keep trying. Each night is a new opportunity. The body keeps trying each night, even if the day felt messy. No matter how stressed you are, no matter how poorly you slept the night before, when night comes again, your body will make another attempt. Adenosine will accumulate, building sleep pressure. Your circadian clock will keep ticking, signaling when it's time to rest. Your body will cool, your brain will prepare, and sleep will become possible again. This persistence is remarkable. Your body doesn't give up on sleep. It doesn't stop trying just because last night was difficult. It keeps showing up, night after night, offering you another chance. You can think of sleep as the brain's way of turning experience into something stored and softened. During the day, you're constantly taking in new information, having new experiences, feeling new emotions. Some of it is overwhelming, some of it is confusing, some of it is painful. Sleep is when your brain takes all of that raw material and begins to process it, to organize it, to integrate it into your existing sense of self and world. The sharp edges get filed down. The intensity fades. What remains is memory without the full emotional charge, experience that you can think about without being overwhelmed by it. Sleep turns chaos into narrative, experience into knowledge. The next day doesn't require perfect sleep, just enough to begin again. You don't need to feel completely refreshed, bursting with energy. as though you've been magically reset. That's a nice feeling when it happens, but it's not the standard you need to meet. You just need enough restoration to face the new day, to engage with what's in front of you, to move forward. Some days you'll feel great. Some days you'll feel tired. That's normal. That's life. What matters is that you keep going, that you don't let one difficult night define how you feel about yourself or your ability to function. You're more resilient than you think. The quiet of night can feel big, but it's also where the nervous system resets. Nighttime can be lonely. The world is dark and still. If you're lying awake, it can feel like you're the only person in the world who's struggling, the only one who can't sleep. But the quiet isn't your enemy. It's necessary. It's the space your nervous system needs to settle, to discharge the accumulated tension of the day, to return to baseline. In the daytime, there's constant stimulation, constant demand. At night, that demand lifts. Your nervous system has room to breathe, to reset itself. Even if sleep is elusive, the quiet is doing its work. Your breath is a steady clock your body understands without effort. Breathing is always with you, automatic and reliable. It doesn't require thought or skill. You don't have to remember how to do it. Your body knows, and your breath is intimately connected to your state of arousal. Fast, shallow breathing signals stress or alertness. Slow, deep breathing signals calm. You can use this connection intentionally, focusing on your breath. Allowing it to slow and deepen sends a signal to your nervous system. It's safe. There's no danger. It's okay to relax. Your breath becomes an anchor, something to return to when your mind starts to wander or worry, a gentle reminder that you're okay, that you're here, that this moment is manageable. Your mind can let thoughts pass like background noise, noticed, then released. Thoughts will come. That's what minds do. You can't stop them, and trying to stop them usually just makes them louder. But you can change your relationship to them. Instead of engaging with every thought, turning it over, analysing it, trying to solve it, you can let it pass. Notice it. Yes, there's a thought about tomorrow's meeting. There's a worry about that conversation. There's a random memory from years ago, and then let it go. Don't fight it. Don't follow it. Just let it move through your awareness like a cloud passing across the sky. The thought was there and now it's gone, and you, now, remain, breathing, resting, present. Sleep has carried humans through millions of nights, and it can carry you tonight too. You're not the first person to lie awake wondering if sleep will come. You're not the first to feel anxious or worried or uncertain. Countless people, across countless generations, have faced the same struggle, and sleep has carried them through. It's older than your worries, stronger than your doubts, more patient than your frustration. It's woven into your biology, built into your brain, as fundamental as your heartbeat. Trust it. Trust that your body knows what to do. Trust that sleep is still there, waiting, ready to catch you when you're ready to let go. Just one more small fact, and then we drift. The words fade now. The explanations complete themselves and step quietly back. What remains is simple. Your body in this moment. The soft weight of blankets, the gentle rhythm of your breathing. Nothing more is required of you. The science has been told. The facts have been laid out one by one, a gentle path through the territory of sleep. Now the path ends, and the night continues, and you are free to let go. Sleep is not far. It has been here all along, patient and certain, waiting for you to stop reaching and simply rest. The night holds you, your breath carries you, and somewhere between one breath and the next, without trying, without knowing the moment it happens, you drift. The next story is about to begin. Please relax and enjoy. Light is a form of energy that can travel through space without needing air. This simple fact is worth pausing on for a moment, because it tells us something fundamental about the universe. Most things we experience in daily life, sound, scent, the feeling of wind, all depend on matter to move from one place to another. Sound needs molecules to bump into each other, carrying vibrations through air or water or solid materials. But light is different. Light can cross the vast emptiness between stars and reach us here on Earth, travelling through regions where there is essentially nothing at all. This ability makes light one of the universe's most elegant messengers, carrying information across distances so large they dwarf our everyday sense of scale. The kind of light our eyes see is only a small slice of a much bigger family called the electromagnetic spectrum. When we use the word light in casual conversation, we usually mean the visible light that lets us see colours and shapes, and the world around us. But visible light is just one narrow band in a much broader continuum of electromagnetic radiation. This family includes radio waves, microwaves, infrared radiation, visible light, ultraviolet light, X-rays, and gamma rays. All of them related, all of them part of the same fundamental phenomenon, just expressed at different scales of energy and wavelength. Our eyes happen to evolve sensitivity to a particular slice of this spectrum, the slice that happens to be abundant in sunlight and useful for navigating our world. Light can be described as an electromagnetic wave, ripples of electric and magnetic fields. Imagine a wave moving through water, where the surface rises and falls in a regular pattern. Light is somewhat similar, except instead of water rising and falling, it is electric and magnetic fields that oscillate, strengthening and weakening in coordinated rhythm as they propagate through space. These fields are not made of matter, they are properties of space itself, rippling outward from their source. The electric field and magnetic field are perpendicular to each other and also perpendicular to the direction the wave travels, creating a kind of self-sustaining pattern that can move through a vacuum without any medium to support it. Light also behaves like tiny packets of energy called photons. This is where things start to get interesting in a gentle, non-urgent way. For a long time, scientists debated whether light was a wave or a particle. The answer turned out to be that light is both, or rather it exhibits properties of both depending on how you observe it. A photon is a quantum of light, a discrete bundle of electromagnetic energy. When light interacts with matter, when it is absorbed by an atom or emitted from one, it does so in these individual packets. Each photon carries a specific amount of energy determined by the frequency of the light. Higher frequency means more energy per photon, lower frequency means less. A photon has no rest mass, which helps explain why it moves at the universe's speed limit. This is a subtle but profound point. Most objects we encounter have mass, and the faster they move, the more energy it takes to accelerate them further. But photons are different. Because they have no rest mass, they do not experience the same resistance to motion. In fact, photons cannot be at rest at all. They must always be moving at the speed of light in whatever medium they happen to be travelling through. In a vacuum, that speed is absolute and unchanging, a fundamental constant woven into the fabric of space-time itself. In a perfect vacuum, light travels at about 300,000 kilometers per second. To put that in perspective, light could circle the Earth's equator more than 7 times in a single second if it were travelling in a straight loop. This speed is often represented by the letter c in physics equations, and it appears in many of the most important relationships in modern physics. The speed of light is not just a speed, it is a cosmic speed limit, a boundary that governs how quickly information and influence can propagate through the universe. That speed is the same no matter how fast the source is moving, which is one of the strangest and most important facts in physics. If you are standing still and someone shines a flashlight at you, the light approaches you at the speed of light. If that person is running toward you while shining the flashlight, the light still approaches you at exactly the same speed. This seems impossible based on our everyday experience with moving objects. If someone throws a ball while running, the ball moves faster relative to you than if they threw it while standing still. But light does not work that way. This constancy of the speed of light is one of the central insights of Einstein's theory of special relativity, and it leads to many of the non-intuitive consequences of that theory, including time dilation and length contraction. Light takes time to travel, so seeing anything is always seeing it slightly in the past. When you look at an object across the room, you're seeing it as it was a tiny fraction of a second ago, the time it took for light to bounce off the object and reach your eyes. For nearby objects, this delay is so small it has no practical impact on your experience, but the principle is the same whether you're looking at a lamp across the room or a star across the galaxy. Every observation you make is necessarily a glimpse into the past, a record of where things were and what they were doing when the light you're receiving first began its journey toward you. Even your reflection in a mirror is delayed by a tiny fraction of a second. The light leaving your face must travel to the mirror and then back to your eyes. If the mirror is 1 meter away, the round trip is 2 meters, and light covers that distance in about 6 billionths of a second. You will never notice this delay in daily life, but it is there, a quiet reminder that the universe operates on timescales far faster and far slower than the ones we are built to perceive directly. Light is not only brightness, it can carry information, heat, and momentum. When sunlight falls on your skin, you feel warmth because the light is transferring energy to you. When light strikes the surface of a spacecraft, it exerts a tiny push, a pressure that can be measured and even used for propulsion in the form of solar sails. And when light enters your eye or a camera sensor, it carries detailed information about the world, information encoded in the patterns of intensity and colour across different parts of the image. Light is a carrier, a medium, a messenger, and it does all of this without ever needing to rest or slow down on its own. Just one more small fact, and then we drift. Colour is your brain's interpretation of different wavelengths of visible light. When you see a red apple, you are not seeing redness as an objective property out there in the world. You are seeing your brain's response to a particular range of wavelengths reflected by the apple's surface. The apple itself is simply interacting with light in a certain way, absorbing some wavelengths and reflecting others. What happens next, the experience of colour, occurs inside you, constructed by your visual system from the raw information delivered by light. Red light has longer wavelengths than blue light. Wavelength is the distance between successive peaks in the wave pattern of light. Red light typically has wavelengths around 650 to 700 nanometers, where a nanometer is 1 billionth of a meter. These wavelengths are longer and more stretched out compared to the waves of blue light, and this difference in wavelength corresponds to a difference in energy and in how our eyes respond. Blue light has shorter wavelengths and higher frequency than red light. Blue wavelengths are typically around 450 to 500 nanometers, roughly half the wavelength of red light. Because the waves are more tightly packed, more of them pass a given point per second. This is what we mean by higher frequency. Frequency and wavelength are inversely related. Shorter wavelengths mean higher frequency, and higher frequency means more energy per photon. So a photon of blue light carries more energy than a photon of red light. White light is usually a mix of many wavelengths together. When you see something that looks white, your eyes are detecting a relatively even blend of different wavelengths across the visible spectrum. Your brain interprets this balanced mixture as white. White is not a single wavelength, but rather the result of many wavelengths arriving together in roughly equal proportions. Sunlight looks white, but it contains a wide range of colours blended together. If you could somehow separate sunlight into its components, if you could take it apart and look at each wavelength individually, you would find that it is made of red, orange, yellow, green, blue and violet light, along with many subtle shades in between. These colours are usually invisible to you because they arrive all at once, mixed together, producing the bright white or slightly warm glow we associate with daylight. A prism separates light because different wavelengths bend by slightly different amounts. When light enters a prism, a piece of glass or other transparent material with flat, angled surfaces, it slows down and changes direction. This bending is more pronounced for shorter wavelengths like blue and violet, and less pronounced for longer wavelengths like red. As a result, the different colours spread out, fanning into a spectrum. The prism does not create the colours, it simply reveals them by separating what was already there. This bending is called refraction. Refraction occurs whenever light passes from one material into another at an angle, and the two materials have different optical properties. The light changes speed as it crosses the boundary, and this change in speed causes the light's path to bend. Refraction is responsible for many everyday optical effects, from the way lenses focus light to the reason a pool looks shallower than it really is when you look down into the water. Water droplets can act like tiny prisms, helping create rainbows. When sunlight enters a raindrop, it refracts, bending as it slows down inside the water. Some of that light then reflects off the back inner surface of the droplet, and then refracts again as it exits the droplet. Because different wavelengths refract by different amounts, the light spreads into colours. Countless droplets, each doing this individually, together create the arc of colour we see stretched across the sky. A rainbow is light being refracted inside droplets, and spread into colours. The rainbow is not an object located at a specific place in the sky. It is an optical phenomenon, a pattern of light that depends on your viewpoint, the position of the sun behind you, and the presence of water droplets in the air in front of you. If you move, the rainbow appears to move as well, because you are changing which droplets are sending their separated colours toward your eyes. The same white light splitting effect can happen in glass, crystals, and even thin layers of oil. Any transparent material with the right geometry and refractive properties can spread light into a spectrum. The iridescent colours you sometimes see on soap bubbles or on a thin slick of oil floating on water come from a different but related process, interference. But the basic principle that light can be split into colours by interacting with matter is the same. Light is always carrying its full range of wavelengths, it just takes the right conditions to reveal them. Just one more small fact, and then we drift. Light moves slower in materials like water or glass than it does in a vacuum. In a vacuum, light travels at its maximum speed, about 300,000 kilometers per second. But when light enters a material, when it moves through water, glass, diamond, or any transparent substance, it appears to slow down. The speed of light in water is about 3/4 of its speed in a vacuum. In glass, it is even slower, depending on the type of glass. In diamond, light slows to less than half its vacuum speed. The slowing is really light interacting with atoms in the material in a way that delays its progress. What is happening at a microscopic level is that photons are being absorbed and re-emitted by the atoms in the material over and over again as the light makes its way through. Each absorption and re-emission takes a tiny amount of time, and the cumulative effect of countless interactions is that the light takes longer to cross a given distance than it would in empty space. The photons themselves always move at the speed of light between interactions, but the start-stop process of absorption and re-emission creates an effective slowdown. This is why refraction happens when light enters a new material. When light crosses a boundary between two materials, say, from air into water, it changes speed. If the light hits the boundary at an angle, one part of the wavefront enters the new material and slows down before the other part does. This causes the wavefront to tilt, bending the direction of the light's path. The amount of bending depends on how much the speed changes and the angle at which the light strikes the boundary. A straw looks bent in a glass because light changes direction, as it moves from water to air. When you look at a straw sitting in a glass of water, the part of the straw underwater appears shifted compared to the part above the water. This happens because light travelling from the submerged part of the straw to your eyes bends as it exits the water and enters the air. Your brain assumes light travels in straight lines, so it interprets the bent light as coming from a location slightly different from where the straw actually is. The straw itself is perfectly straight, but the light's journey is not. Lenses work by bending light in controlled ways. A lens is a piece of transparent material, usually glass or plastic, shaped so that it refracts light in a specific pattern. A convex lens, thicker in the middle than at the edges, bends light inward, causing rays of light to converge toward a focal point. A concave lens, thinner in the middle, bends light outward, causing rays to diverge. By carefully shaping the surfaces of a lens, you can control how light is directed, allowing you to focus images, correct vision, or magnify distant objects. Your eyes use a lens to focus light onto the retina. The lens in your eye is a flexible, transparent structure located behind the pupil. It works together with the cornea, the clear outer layer at the front of your eye, to bend incoming light and form a sharp image on the retina, the light-sensitive layer at the back of your eye. The retina contains cells that respond to light and send signals to your brain, where the signals are interpreted as vision. Without the lens to focus the light, the image reaching your retina would be blurry and indistinct. Cameras work similarly, using lenses to focus light onto a sensor. A camera lens gathers light from the scene in front of it, and bends that light so it converges at a specific distance behind the lens, where a sensor or piece of film is positioned. The sensor records the pattern of light and dark, along with the variations in colour, creating a photograph. The principles are the same as in your eye. Gather light, bend it with a lens, focus it onto a surface that can record or respond to the light. Light can travel along curved paths in materials like fibre optics. A fibre optic cable is a thin strand of glass or plastic designed to guide light over long distances. Even though the cable may bend and twist, light stays inside, following the curves of the fibre. This is possible because of total internal reflection. a phenomenon where light striking the inner surface of the fibre at a shallow angle reflects back into the fibre instead of escaping. Fibre optics guide light mostly through internal reflection. When light travels through a fibre optic cable, it bounces off the walls of the fibre again and again, zigzagging its way forward while remaining confined within the fibre. This allows light to carry information, such as phone calls or internet data, across cities and even across oceans with minimal loss. The light pulses on and off rapidly, encoding information in patterns of brightness, and those patterns are decoded at the other end of the cable. This allows information to be carried long distances using pulses of light. Fibre optic communication is faster and more efficient than older methods that relied on electrical signals travelling through metal wires. Light pulses can carry more information in a given amount of time, and they are less susceptible to interference from electromagnetic noise. As a result, much of the world's communication infrastructure now relies on light travelling through hair-thin strands of glass, moving data at speeds close to the speed of light in glass. Just one more small fact, and then we drift. A mirror reflects light in a very orderly way from a smooth surface. When light strikes a mirror, nearly all of it bounces back at an angle equal to the angle at which it arrived. This predictable behaviour is called specular reflection. The smoothness of the mirror's surface is key, because the surface is so flat and even at a microscopic level, the reflected light maintains the same pattern it had before striking the mirror. That is why you can see a clear, undistorted image in a mirror. Rough surfaces scatter light in many directions, which is why most objects don't look mirror-like. A piece of paper, a painted wall, Earth's wooden table, all of these have surfaces that are rough at a small scale, even if they feel smooth to the touch. When light hits these surfaces, it reflects in many different directions, a process called diffuse reflection. This scattering is what allows you to see the object from various angles. If the wall only reflected light in one direction like a mirror, you would only see an image in it from a very specific viewpoint. The scattering makes the object visible from all around. When light is absorbed, its energy is often converted into heat. Not all light that strikes an object is reflected or transmitted. Some of it is absorbed by the material. When a photon is absorbed, its energy is transferred to the atoms or molecules in the material, causing them to vibrate more vigorously. This increased vibration is heat. The more light an object absorbs, the warmer it tends to become. This is why you can feel the warmth of sunlight on your skin, or notice that a dark car parked in the sun is hot to the touch. Dark surfaces absorb more visible light and often warm up faster in sunlight. A black surface absorbs a large portion of the wavelengths of visible light that strike it, converting that energy into heat. A white surface, by contrast, reflects most of those wavelengths, absorbing less and therefore heating up more slowly. This is why light-coloured clothing is often cooler to wear in summer, and why dark asphalt can become uncomfortably hot on a sunny day. Light-coloured surfaces reflect more visible light and often stay cooler. White objects reflect many wavelengths fairly evenly across the visible spectrum, sending much of the incoming light back into the environment rather than absorbing it. This reflection helps keep the surface cooler, because less energy is being converted into heat within the material. A red object looks red because it reflects more red wavelengths and absorbs many others. The pigments or dyes in the object's surface selectively absorb certain wavelengths, often blues and greens, while reflecting the longer wavelengths we perceive as red. The colour you see is determined by which wavelengths escape the object and enter your eyes. The object is not generating red light. It is simply filtering the white light that illuminates it, letting some wavelengths bounce away and trapping others. A black object looks black because it absorbs most visible wavelengths. Black is the absence of reflected light, at least in the visible range. A perfectly black object would absorb all visible light completely, reflecting nothing back. In practice, no object is perfectly black, but dark surfaces come close, absorbing the vast majority of wavelengths and reflecting very little. A white object looks white because it reflects many wavelengths fairly evenly. White is the presence of light across the spectrum, balanced in such a way that your eye interprets it as colourless brightness. A surface that reflects all wavelengths equally looks white to you. If it reflected only some wavelengths, you would see it as coloured. Transparent materials let many wavelengths pass through, though not always perfectly. Glass, water, and clear plastic allow light to travel through them with relatively little scattering or absorption. This transparency makes them useful for windows, lenses, and containers. But even transparent materials interact with light to some degree. They may absorb certain wavelengths, or they may scatter light slightly, which is why thick glass or a deep pool of water can take on a tint or appear less than perfectly clear. Transparent does not mean invisible. It means light can travel through it without being scattered too much. A pane of glass is transparent, but you can still see the glass itself under the right conditions, perhaps as a reflection or as a slight distortion in the view beyond it. Transparency is about the ability of light to pass through, not about the material ceasing to exist visually. Just one more, small fact, and then we drift. The sky looks blue mainly because air molecules scatter blue light more than red light. As sunlight enters Earth's atmosphere, it encounters countless molecules of nitrogen and oxygen. These molecules are much smaller than the wavelength of visible light, and when light waves interact with such small particles, shorter wavelengths are scattered more strongly than longer wavelengths. Blue light, with its shorter wavelength, is scattered in all directions much more effectively than red light. As you look up at the sky, you see this scattered blue light coming from all parts of the atmosphere above you. This scattering is stronger for shorter wavelengths, like blue. The scattering process, called Rayleigh scattering, depends on the size of the scattering particles and the wavelength of the light. For particles much smaller than the wavelength, as air molecules are, the amount of scattering is inversely proportional to the fourth power of the wavelength. That means blue light, being about half the wavelength of red light, is scattered roughly 16 times more strongly. This dramatic difference is why the sky appears blue rather than some other colour. At sunrise and sunset, light travels through more atmosphere before reaching you. When the sun is low on the horizon, its light must pass through a much thicker slice of Earth's atmosphere compared to when the sun is directly overhead. This longer path gives air molecules more opportunity to scatter the shorter wavelengths out of the direct beam of sunlight. More atmosphere means more scattering, leaving more reds and golds in the direct light. By the time sunlight has travelled through all that extra atmosphere, much of the blue and green light has been scattered away in other directions. What remains, and what reaches your eyes, is enriched in the longer wavelengths, the reds, oranges, and yellows. This is why the sun itself can look deep orange or red near the horizon, and why the sky around it glows with warm colours. This is why sunsets often look warm and glowing. The light reaching you at sunset has been filtered by the atmosphere, stripped of its blues and greens, leaving behind a spectrum that feels warm and gentle. The colours shift gradually as the sun sinks lower, and the exact hues you see depend on the amount of dust, water vapour, and other particles in the atmosphere, all of which can scatter and absorb light in different ways. Clouds look white because water droplets scatter many wavelengths at once. The droplets that make up a cloud are much larger than air molecules, large enough that they scatter all wavelengths of visible light roughly equally. This even scattering across the spectrum produces white light, so clouds appear white or grey depending on their thickness and the angle of the light. A thin cloud scatters light, but still lets much of it pass through, so it looks bright white. A thicker cloud scatters and absorbs more light, so less. Light reaches your eyes, and the cloud looks darker. Storm clouds can look dark because they're thicker and block more light from passing through. A towering storm cloud contains a great deal of water, ice, and sometimes even larger particles, all of which scatter and absorb light. By the time sunlight has made its way through the depths of the cloud, much of it has been absorbed or scattered back upward, leaving less light to illuminate the underside of the cloud. From below, this makes the cloud look dark and heavy. Fog is made of tiny droplets that scatter light and soften contrast. When fog fills the air, visibility drops because light is scattered in all directions by the countless droplets suspended in the air. This scattering blurs edges and reduces the sharpness of distant objects, giving the world a soft, diffuse quality. Objects fade into the fog as their light is scattered before it can reach your eyes, and the overall effect is one of muted tones and gentle obscurity. The golden hour look happens when sunlight is warmer and shadows are longer. The term golden hour refers to the time shortly after sunrise or before sunset, when the light is soft, warm, and flattering. The sun is low, so the light has travelled through more atmosphere, giving it that warm colour. The angle of the light also means shadows stretch out long and gentle, creating depth and texture in the landscape. Photographers often seek out these times for the quality of light they provide. The moon shines mostly by reflecting sunlight, not by making its own. The moon does not generate light. It is a rocky body that simply reflects the light of the sun back toward Earth. What you see when you look at the moon is sunlight that has travelled from the sun to the moon's surface, bounced off, and then travelled to your eyes. The moon's surface is not very reflective. It absorbs much of the light that hits it, but enough light bounces back to make the moon visible and sometimes even bright enough to cast shadows on Earth at night. Just one more small fact, and then we drift. Light behaves like a wave in many experiments and like a particle in others. This dual nature puzzled scientists for a long time. Some experiments, like those involving interference and diffraction, seemed to show that light was clearly a wave. Other experiments, like the photoelectric effect, where light knocks electrons out of a metal surface, seemed to show that light was clearly made of particles. The resolution is that light is neither purely a wave nor purely a particle. It is something more fundamental, a quantum entity that exhibits both kinds of behaviour depending on what you are measuring. This is called wave-particle duality. The term captures the idea that light does not fit neatly into the classical categories of wave or particle. Instead, light has aspects of both, and which aspect is more apparent depends on the context and the way you observe it. This duality is not unique to light. Matter too exhibits wave-like properties under the right conditions, but it is especially clear and important in understanding how light works. In the double-slit experiment, light can create an interference pattern like waves do. If you shine light through two narrow slits cut in an opaque screen, and then observe the pattern that forms on a surface beyond the slits, you do not see just two bright lines corresponding to the two slits. Instead, you see a pattern of many bright and dark bands. This pattern is characteristic of waves interfering with each other. Where the waves from the two slits overlap in phase, they reinforce and create a bright band. Where they overlap out of phase, they cancel and create a dark band. Light is clearly behaving like a wave in this experiment. Yet light also arrives as individual photons, like particles. If you turn the intensity of the light way down so that photons pass through the slits one at a time, you might expect the interference pattern to disappear. But it does not. Each photon lands at a specific point on the screen, like a particle. Yet over time, as more and more photons arrive one by one, the pattern that builds up is the same interference pattern you saw with bright light. Each photon somehow knows about both slits, even though it seems to pass through as a single localized particle. This is one of the deep mysteries of quantum mechanics, and it reminds us that the quantum world does not always align with our everyday intuitions. Interference happens when waves overlap and reinforce or cancel each other. If two waves arrive at the same place at the same time, and their peaks line up, they add together and create a wave with a larger amplitude. This is constructive interference. If the peak of one wave lines up with the trough of another, they subtract and can cancel out. This is destructive interference. Light waves can interfere with each other just like waves on water or sound waves, and this interference is responsible for many optical effects, from the colours in soap bubbles to the precise measurements made by interferometers. Diffraction is light spreading out when it passes through a small opening or around an edge. When light encounters an obstacle or a narrow slit, it does not simply cast a sharp shadow. It bends around the edges and spreads into regions that would be in shadow if light travelled only in perfectly straight lines. This bending is diffraction, and it is a hallmark of wave behaviour. The smaller the opening relative to the wavelength of light, the more pronounced the diffraction. This is why sharp shadows are rarely perfectly sharp at tiny scales. If you look closely at the edge of a shadow, perhaps the shadow of a straight edge cast by a bright distant light source, you will notice that the boundary is not razor sharp. There is a gradual transition from light to dark, with subtle patterns of brightness near the edge. This is diffraction at work, blurring the boundary and revealing the wave nature of light. Polarization is when light waves line up more in one direction. Light is a transverse wave, meaning the oscillations of the electric and magnetic fields occur perpendicular to the direction the light is travelling. Unpolarized light has these oscillations occurring in all possible perpendicular directions, jumbled together. Polarized light has the oscillations aligned more in one particular direction. Polarization can occur naturally, such as when light reflects off a surface, or scatters in the atmosphere, or it can be created artificially using polarizing filters. Polarized sunglasses reduce glare by blocking certain orientations of light. When light reflects off a flat surface like water or a road, it tends to become partially polarized, with the electric field oscillations more aligned horizontally. Polarized sunglasses have filters that block horizontally polarized light while allowing vertically polarized light to pass through. This selectively reduces the brightness of the reflected glare while allowing you to see other light normally, making it easier to see into water or drive on a sunny day without being blinded by reflections. Many animals can sense polarization patterns in the sky for navigation. Some insects, birds, and marine animals have evolved the ability to detect the polarization of sunlight, which forms predictable patterns in the sky depending on the sun's position. Even on a cloudy day when the sun itself is not visible, these polarization patterns can provide directional cues. This gives these animals a kind of compass, a way to orient themselves using information that is invisible to human eyes. Just one more small fact, and then we drift. A laser produces light that is unusually orderly and synchronized. The word laser stands for light amplification by stimulated emission of radiation, which describes the process by which a laser generates light. In a laser, atoms or molecules are energized and then encouraged to release their energy as photons in a coordinated way. The result is light in which all the photons are marching in step. They have the same wavelength, they are in phase with one another, and they travel in the same direction. This makes laser light very different from the light produced by an ordinary bulb or the sun, where photons are emitted randomly with a mix of wavelengths and directions. This orderliness is called coherence. Coherent light maintains a consistent phase relationship over time and distance. In practical terms, this means that laser light can be focused to a very tight spot, can travel long distances without spreading out much, and can produce clear interference patterns when combined with other laser beams. Coherence is what makes lasers so useful in applications that require precision and control. Laser light is often very narrow in wavelength, meaning it's close to a single color. Most lasers produce light within a very narrow range of wavelengths, sometimes so narrow that the light appears to be a single pure color. A red laser pointer, for example, emits light at a wavelength of around 630 to 680 nanometers, depending on the type of laser. This monochromaticity is another defining feature of laser light, and it makes lasers valuable in situations where you need a specific wavelength for a specific purpose. Lasers can travel long distances without spreading out much. Ordinary light spreads in all directions as it travels away from its source. A flashlight beam gets wider the farther it goes. But a laser beam, because it is so well collimated, meaning its light rays are nearly parallel, spreads much more slowly. This allows a laser beam to remain narrow and intense over great distances. Laser beams have been bounced off mirrors left on the moon by astronauts, allowing scientists on Earth to measure the distance to the moon with extraordinary precision. Laser technology is used in barcode scanners, surgery, and communication systems. In a barcode scanner, a laser beam reflects off the pattern of black and white bars, and a sensor reads the variations in reflected light to decode the information in the barcode. In surgery, lasers can cut tissue with precision or deliver energy to specific locations without affecting surrounding areas. In communication systems, lasers send pulses of light through fiber optic cables, carrying vast amounts of data across continents and under oceans. Lasers have become so integrated into modern technology that it is easy to overlook how remarkable and versatile they are. Light can carry information by changing its intensity, frequency, or timing. Any property of light that can be controlled and measured can be used to encode information. You can make light brighter and dimmer in a pattern. This is amplitude modulation. You can shift the wavelength slightly. This is frequency modulation. You can turn the light on and off in rapid pulses. This is pulse modulation. Whichever method you use, the basic principle is the same. Light becomes a carrier of information, and the information is extracted at the other end by measuring how the light has been changed. Remote controls often use infrared light your eyes can't see. Infrared light has wavelengths just longer than the red end of the visible spectrum, typically from about 700 nanometers to 1 millimeter. Your eyes cannot detect infrared, but cameras and sensors can. When you press a button on a remote control, a small infrared LED inside the remote flashes in a specific pattern, encoding the command. the sensor in your television or other device detects the pattern and responds accordingly. Infrared light is convenient for remote controls because it is invisible to you, so it does not produce any distracting flashes, and it does not interfere with visible light in the room. Wi-Fi is not light, but it is part of the same electromagnetic family as visible light. Wi-Fi uses radio waves, which have wavelengths much longer than visible light, typically a few centimeters. But radio waves and visible light are both forms of electromagnetic radiation, differing only in wavelength and energy. They obey the same physical laws, and they both travel at the speed of light in a vacuum. The electromagnetic spectrum is a continuum, with no hard boundaries between the regions we call radio, microwave, infrared, visible, ultraviolet, and so on. The electromagnetic spectrum includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each of these regions corresponds to a different range of wavelengths and photon energies. Radio waves have the longest wavelengths and the lowest energies. Gamma rays have the shortest wavelengths and the highest energies. In between, you find the other familiar forms of electromagnetic radiation, each with its own properties and uses. Microwaves heat food by causing water molecules to vibrate. Ultraviolet light from the sun can damage skin and cause sunburn. X-rays can pass through soft tissue but are absorbed by bone, making them useful for medical imaging. Visible light is just the small band our eyes evolved to detect well. The wavelengths we call visible range from about 400 to 700 nanometers, a tiny sliver of the electromagnetic spectrum. Our eyes evolved to be sensitive to this range because it happens to be where the sun's radiation is most intense at Earth's surface, and because this range includes wavelengths that interact usefully with the chemistry of life. But visible light is not special in any fundamental sense. It is simply the part of the spectrum we happen to be able to see directly. Just one more small fact, and then we drift. Sunlight takes about 8 minutes to reach Earth. The Sun is roughly 150 million kilometers away from Earth, a distance called an astronomical unit. Light, travelling at 300,000 kilometers per second, covers that distance in about 8 minutes and 20 seconds. This means that the sunlight warming your face right now left the sun more than 8 minutes ago. You're not seeing the sun as it is at this moment. You're seeing it as it was 8 minutes in the past. That means the sun you see is the sun from 8 minutes ago. If something dramatic were to happen on the sun, a sudden change in brightness, or an eruption of plasma, you would not know about it for at least 8 minutes, because that is how long it would take for the light carrying that information to reach you. This delay is a fundamental consequence of the finite speed of light, and it applies to everything you observe, near or far. Starlight can take years, centuries, or thousands of years to reach you. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. A light-year is the distance light travels in 1 year, about 9 trillion kilometers. So when you see Proxima Centauri, you are seeing it as it was 4 years ago. Other stars are much farther. Some of the stars you can see in the night sky are hundreds of light-years away, and some are thousands of light-years away. Their light has been travelling through space for longer than human civilizations have existed. Some of the light you see from galaxies began travelling millions of years ago. Galaxies are vast collections of stars, gas and dust, and most of them are incredibly far away. The Andromeda Galaxy, the nearest large galaxy to our own Milky Way, is about 2.5 million light-years away. When you look at Andromeda, you're seeing light that left that galaxy 2.5 million years ago, long before modern humans existed. More distant galaxies are even farther, some so far that their light has been travelling for billions of years. Looking into space is also looking back in time. Astronomy is unique among the sciences in this way. When astronomers observe distant objects, they are not just learning about faraway places, they are also learning about the past. The farther out they look, the farther back in time they see. This allows astronomers to study the history of the universe, to observe galaxies as they were when the universe was young, and to trace the evolution of cosmic structures over billions of years. Some stars you can see may have changed or even ended since their light began its journey. A star you see tonight might have exploded in a supernova centuries ago, but the light from that explosion has not yet reached Earth. You are seeing the star as it was, not as it is. This is a strange and humbling thought. that the stars themselves are not quite where they appear to be, and their present condition is hidden from us by the time it takes light to cross the distances of space. Nebulae glow because gas is energized by nearby stars and then releases light. A nebula is a cloud of gas and dust in space, often vast and diffuse. Some nebulae shine because they are illuminated by nearby hot stars. The ultraviolet light from these stars energizes the atoms in the nebula, knocking electrons into higher energy states. When the electrons fall back down to lower energy states, they emit light at specific wavelengths determined by the type of atom. Hydrogen, for example, emits a characteristic red light, which is why many nebulae have a reddish glow. Some nebulae reflect light, and others emit their own light from energized atoms. A reflection nebula scatters the light of nearby stars, appearing blue because shorter wavelengths scatter more effectively, just as in Earth's atmosphere. An emission nebula glows with its own light, produced by atoms releasing energy. Both types are beautiful, and both reveal information about the composition and physical conditions in these clouds. Dust in space can block light and create dark patches in the sky. Not all the material in space is gas. There are also tiny solid particles, dust grains made of carbon, silicates, and other materials. These grains can absorb and scatter light, making the regions behind them appear dark. Dark nebulae are clouds of dust so thick that they obscure the stars beyond. They appear as dark patches against the bright background of the Milky Way. These regions are often sites of star formation, where gravity is pulling gas and dust together to form new stars. Space is not truly empty. It contains gas, dust, radiation, and faint light travelling in every direction. Even in the vast spaces between stars there is matter, thin and tenuous but present. There is light too from distant stars and galaxies, cosmic background radiation left over from the Big Bang, and high-energy particles called cosmic rays streaming through the galaxy. Space is not a featureless void. It is a dynamic environment, full of subtle activity on scales both enormous and tiny. Just one more small fact, and then we drift. Gravity can bend the path light takes through space. According to Einstein's general theory of relativity, gravity is not a force in the traditional sense, but rather a curvature of space-time caused by the presence of mass and energy. Light, despite having no mass, is affected by this curvature. When light passes near a massive object such as a star, a galaxy, or a black hole, it follows the curved geometry of space-time, and its path bends. This bending is real and measurable, and it has profound implications for our understanding of the universe. This bending is called gravitational lensing. Just as a glass lens bends light to form an image, a massive object can bend light from more distant sources, creating distorted, magnified, or multiple images. Gravitational lensing was first observed during a solar eclipse in 1919, when stars near the Sun appeared shifted from their usual positions because the Sun's gravity bent their light. This observation provided one of the first confirmations of general relativity. A massive object can act like a lens, warping the light from something behind it. If a distant galaxy lies behind a massive cluster of galaxies from our perspective, the light from the distant galaxy must pass through the curved space-time around the cluster to reach us. The cluster acts as a gravitational lens, bending the light and often producing distorted or multiple images of the background galaxy. This can make the background object appear brighter and larger than it would otherwise, allowing astronomers to study objects that would be too faint and small to see otherwise. Lensing can make distant galaxies look stretched, smeared, or multiplied. The exact effect depends on the alignment of the observer, the lensing mass, and the background object, as well as the distribution of mass in the lens. Sometimes, the images are arcs of light stretched around the lensing object. Sometimes there are multiple images of the same background galaxy arranged symmetrically. In rare cases, the geometry is just right to produce a ring of light called an Einstein ring, where the light from a distant source is bent into a circle around the lens. Scientists use lensing to map mass in the universe, including mass we can't see directly. Not all mass emits light. Dark matter, for example, does not emit, absorb, or reflect light, but it does have mass, and therefore it does curve space-time. By studying how light is bent as it passes through regions of space, astronomers can infer the distribution of mass, including dark matter. Gravitational lensing has become a powerful tool for mapping the dark matter in galaxy clusters and for studying the large-scale structure of the universe. Light leaving a strong gravitational field loses a bit of energy and shifts toward redder wavelengths. This effect is called gravitational redshift. When a photon climbs out of a deep gravitational well, such as from the surface of a very massive star or near a black hole, it loses some energy. Since a photon's energy is related to its frequency, losing energy means the frequency decreases. Lower frequency corresponds to longer wavelength, so the light shifts toward the red end of the spectrum. This shift is subtle for most objects, but it is measurable and has been confirmed in many experiments and observations. This is called gravitational redshift. It is one of the predictions of general relativity, and it has been tested with great precision. For example, clocks at different altitudes on Earth run at slightly different rates because they are in slightly different gravitational fields. The clock at higher altitude, where gravity is a bit weaker, runs faster than the clock at lower altitude. This difference has been measured using atomic clocks and agrees with the predictions of relativity. Time runs a little slower in stronger gravity compared to weaker gravity. This is time dilation due to gravity, another consequence of space-time curvature. The stronger the gravitational field, the more space-time is curved, and the slower time passes relative to a region with weaker gravity. This is not a malfunction of clocks, it is a real difference in the passage of time itself. Time is not absolute, it is flexible and depends on the gravitational environment. GPS systems correct for time differences related to both motion and gravity. The satellites that make up the global positioning system orbit Earth at high speeds and at high altitudes. Both factors affect the rate at which time passes on the satellites compared to the rate of time passing on the ground. Special relativity predicts that moving clocks run slower, so the satellite's motion would make their clocks run slower than clocks on Earth. But general relativity predicts that clocks in weaker gravity run faster, so the satellite's altitude makes their clocks run faster than clocks on Earth. The net effect is that the satellite's clocks run faster by about 38 microseconds per day. This may sound tiny, but GPS relies on precise timing, and if these corrections were not made, position errors would accumulate rapidly, several kilometers per day. So every day, the GPS system applies corrections to account for relativity. So even everyday navigation depends on careful understanding of light, time, and gravity. The fact that your phone can tell you where you are to within a few meters is a testament to the accuracy of relativity and to the engineers who designed the system to account for the subtle but real effects of space-time curvature. Light, in the form of radio signals traveling between satellites and your receiver, carries the information that makes this possible, and the calculations that turn those signals into your location depend on understanding how time and space behave in the presence of gravity. Just one more small fact, and then we drift. In a dark room, there is still electromagnetic radiation around you, including infrared warmth. Even when the lights are off and the room is pitch black, electromagnetic radiation is present. The walls, the furniture, your own body, all of these emit infrared radiation because they have temperature. Anything above absolute zero gives off thermal radiation, and for objects at room temperature, this radiation falls mostly in the infrared range, invisible to your eyes, but very real. Your body naturally gives off infrared radiation as heat. Your body generates heat through metabolic processes, and that heat radiates away from your skin in all directions. If you were to look at yourself with an infrared camera, you would see a glowing figure, warm and bright against the cooler background. This is not light in the visible sense, but it is light in the broader sense. Electromagnetic radiation, photons carrying energy away from your body. Even when you close your eyes, your brain still responds to light and darkness through internal rhythms. Your eyes do more than allow you to see images. They also send signals to parts of the brain that regulate your sleep-wake cycle and other biological rhythms. Even with your eyes closed, some light can still reach the photoreceptors in your eyes, and your brain keeps track of the general pattern of light and dark over the course of a day. The cycle of light and dark helps guide your circadian clock. Your circadian clock is an internal timekeeping system that aligns your physiology and behavior with the 24-hour day. Light is the most important signal that keeps this clock synchronized with the external world. Bright light, especially in the morning, helps set the clock and promote wakefulness. Darkness, especially in the evening and at night, signals that it's time to wind down and prepare for sleep. Moonlight, streetlights, and screens can subtly affect sleep by signaling daytime to the brain. Artificial light at night, especially light rich in blue wavelengths, can interfere with your circadian rhythms. Your brain interprets this light as a signal that it is still daytime, which can delay the release of melatonin, a hormone that promotes sleepiness. This is why exposure to bright screens before bed can make it harder to fall asleep, and why dim, warm lighting in the evening is often more conducive to rest. Gentle, dim light in the evening often supports the body's natural wind-down signals. Soft, warm light does not stimulate the brain's alertness systems as strongly as bright, blue-toned light. By keeping evening light levels low and warm, you can help your body transition more smoothly from wakefulness to sleep. This is one reason why candlelight or a reading lamp with a warm glow can feel calming at night, while overhead fluorescent lights can feel jarring. The atoms in your body have interacted with starlight at some point in the long history of the universe. The atoms that make up your body were not created on Earth. They were forged in the cores of ancient stars in supernova explosions and in other cosmic events long before the sun and planets formed. Those atoms have travelled through space, mixed with clouds of gas and dust, and eventually found their way into the material that formed the solar system, the Earth, and everything on it, including you. At various points in that journey, photons of starlight pass through those clouds, interacting with atoms in small ways, scattering off them, being absorbed and re-emitted, gently nudging them along. Many of the elements in you were forged in ancient stars and scattered outward, long before your life began. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all of these were created through nuclear fusion in the interiors of stars that lived and died billions of years ago. When those stars reached the end of their lives, some of them exploded as supernovae, scattering their enriched material into space. That material, mixed with other gas and dust, became part of new star-forming clouds, and eventually condensed to form new stars and planets, including our solar system. You're made of stardust, not metaphorically, but literally. Your atoms were born in stars. Light is one way the universe shares its story, quietly, steadily, without urgency. Every photon carries information, a record of where it came from and what it has encountered along the way. The light from distant stars carries clues about their temperature, composition, and motion. The light from the sun has carried energy across space to warm the Earth and power life for billions of years. Light connects everything, past to present, near to far. It is a messenger, a thread running through the cosmos, linking the birth of stars to the beating of your heart. And tonight, you don't need to chase any story at all. Your mind can dim softly, and rest can arrive on its own. The universe will keep moving, light will keep travelling, stars will keep shining, and none of it requires your attention right now. You have learned about light, about how it bends and reflects, how it carries information and energy across unimaginable distances, how it touches everything, including you. But for now, that knowledge can settle gently in the background. You do not need to hold on to it tightly. It will still be there tomorrow. Just one more small fact, and then we drift. Your breath is steady, in and out, slow and easy. Light too moves in waves, rising and falling, travelling onward. But you do not have to follow it. You can let it go. Let the thoughts drift past like clouds. Let the questions fade. Let the world outside continue on its own while you sink into stillness. There is nothing more to figure out right now. No mysteries to solve, no ideas to grasp. Only the gentle rhythm of your breath, the softness of the pillow, the quiet of the room. Light will keep travelling while you rest. Stars will keep shining while you sleep. The universe will carry on patient and endless, and it will still be there when you wake. There is no rush, no urgency. Just the slow, inevitable drift towards sleep, as natural as light moving through space, as gentle as a wave fading into the distance. Let go. Let yourself soften. Let the darkness around you become comfortable and safe, a place where nothing is needed, where everything can wait. Your body is ready to rest. Your mind is ready to let go. And sleep, like light, is already on its way. The next story is about to begin. Please relax and enjoy. Time travel. The phrase itself sounds like science fiction, like something that belongs on movie posters or in pulp novels with bright covers. But tonight, We're going to set aside the dramatic versions and look at what time travel actually means in physics, not as a fantasy, not as an adventure, but as a calm idea experiment. Something to think about softly, the way you might watch rain slide down a window. You're safe in bed, the universe is doing the moving. We're just going to follow along one small fact at a time, letting each idea settle before we move to the next. So what does time travel mean when physicists use the term? In physics, time travel usually means moving through time at a different rate than someone else. That's the core of it. Not teleportation, not magic doorways, just a difference in how fast time passes. And here's the first gentle truth. We all travel forward in time automatically, 1 second per second. Every moment you're moving into the future. Your heartbeat carries you forward, your breath carries you forward. Time is already taking you somewhere, quietly and continuously, without any effort on your part. The mystery, then, isn't whether time travel exists. The mystery is whether you can travel forward faster than normal, or whether you can go backward at all. Those are the two questions physics actually addresses. Forward faster than normal, that one has an answer and it's yes. Backward in time, that one is still open, still speculative, still wrapped in mathematics and uncertainty. But we'll get there slowly, gently, one idea at a time. In science, forward time travel is real in the sense of time dilation. Time dilation is a term that sounds complicated, but the concept is simple. It means two clocks can tick at different speeds. Imagine two identical clocks, perfectly synchronized at the start. Put them in different situations, and they can end up showing different times. Not because one is broken, but because time itself passes differently for them. This isn't a defect, it's a feature of the universe. High speed can make your time pass slightly slower than someone at rest. This is real, it's been measured, it's not metaphorical. If you move very fast relative to someone else, your clock will tick more slowly compared to theirs. The effect is tiny in everyday life, but it's there. Strong gravity can also make time pass slightly slower. Again, this is real. Stand at the base of a mountain and your clock ticks slightly slower than a clock at the peak. The difference is extraordinarily small, but with precise instruments, we can measure it. These effects are tiny in everyday life, but measurable. You will never notice them in your daily routine. Your morning coffee doesn't care about relativity. Your commute doesn't involve speeds where time dilation becomes obvious. But the effects are there, humming quietly in the background of reality, proven over and over again by careful experiments. Now backward, time travel is different. Backward time travel would mean arriving in an earlier moment. It would mean stepping into yesterday or last year or 1,000 years ago. This is not the same as forward time travel. Physics treats backward time travel as speculative, not established. There are mathematical scenarios where it might be possible, but no confirmed mechanism, no blueprint, no clear path from theory to practice. Many time travel ideas come from math solutions, not engineering plans. Einstein's equations allow certain solutions that include closed time-like curves, paths through space-time that loop back on themselves. But a mathematical solution doesn't automatically mean a physical reality. The universe is under no obligation to make every solution accessible. The calm goal tonight is understanding, not proving a fantasy. We're here to learn what's real, what's possible, and what remains in the realm of imagination. Just one more small fact and then we drift. Einstein's relativity links space and time into one fabric, space-time. Before Einstein, space and time seemed separate. Space was the stage, time was the clock that ticked while events unfolded on that stage. But relativity revealed something deeper. Space and time are woven together. They affect each other. They bend and stretch together. When you move through space, you also move through time, and the two are inseparable. In relativity, motion and gravity affect the flow of time. This is not an illusion or a trick of perception. It's built into the structure of the universe. Move differently, and time behaves differently for you. Exist in a different gravitational field, and time behaves differently for you. There is no single universal now shared by all observers. Two people moving differently can disagree about what events are simultaneous. What one person experiences as right now might be slightly in the past or future for someone else. This sounds strange, and it is. Our everyday experience doesn't prepare us for this. We feel like there's one universal present moment, a single now, that everyone shares. But that's only because we move slowly compared to the speed of light, and we live in relatively weak gravity. Zoom out to the scale of the cosmos, or zoom into the behavior of particles moving at high speeds, and the universe reveals its true nature. Time is flexible. Time dilation from speed is called special relativistic time dilation. It arises from the geometry of spacetime in Einstein's special theory of relativity. Time dilation from gravity is called gravitational time dilation. It arises from the curvature of spacetime in Einstein's general theory of relativity. These are two different effects with two different causes, but both result in clocks ticking at different rates. Gravitational time dilation is stronger nearer massive objects. If you're standing on the surface of a planet, you're deeper in a gravitational well than someone orbiting far above. Your time passes slightly more slowly. The effect gets more dramatic the stronger the gravity. Near a black hole, the effect becomes extreme. But even here on Earth, it's real. GPS satellites must account for relativity to stay accurate. This is one of the most practical, everyday confirmations of Einstein's theories. GPS satellites orbit the Earth at high altitude, where gravity is slightly weaker than on the surface. They also move at high speed. Both effects influence the rate at which their onboard clocks tick. If we didn't correct for these relativistic effects, the GPS system would fail, the timing errors would accumulate, and location errors would grow. Within hours, GPS would become unreliable. Within days, it would be useless. Without corrections, GPS timing would drift and location errors would grow. Engineers had to build relativity into the system. They had to account for the fact that time passes differently on the satellite than it does on the ground. This means relativity is not just theory, it's used daily. Every time you navigate with GPS, you're relying on Einstein's understanding of time. Aging slower is not immortality. It's important to be clear about this. Time dilation doesn't make you live forever. It's a difference in elapsed time between paths. If you travel at high speed and return, you will have experienced less time than someone who stayed behind. Your body will have aged less, but you haven't stopped time. You've just taken a different path through space-time, a path where less time elapsed for you. Forward time travel is really skipping ahead relative to others. You age less while the rest of the world ages normally. When you return, you arrive in their future. You've jumped forward, not by magic, but by physics. The universe already allows different rates of time, quietly, continuously. This isn't something we need to invent or discover. It's already there, woven into the fabric of reality. Just one more small fact, and then we drift. Astronauts on the International Space Station age a tiny bit less than people on Earth. The ISS orbits at about 400 kilometers above the surface. At that altitude, gravity is slightly weaker, which makes time pass slightly faster. But the station is also moving at about 28,000 kilometers per hour, which makes time pass slightly slower. These two effects work in opposite directions. The speed effect is stronger, so overall, astronauts on the ISS age slightly less than people on the ground. How much less? Not much. After 6 months on the ISS, an astronaut will have aged about 0.005 seconds less than someone who stayed on Earth. It's a tiny difference, but it's real. It's been measured. It's been confirmed over and over again. Airplane flights create an even smaller time difference. Pilots and flight attendants who spend their careers at cruising altitude, moving at high speed, age very slightly less than people who stay on the ground. The effect is so small that it's irrelevant to daily life, but it's there. These differences are real but extremely small. You can't use them to visit the distant future in any practical sense. But they prove the principle. They demonstrate that time is not absolute. The faster you move, the more noticeable time dilation becomes. If we could build a spaceship that travelled at a significant fraction of the speed of light, the effect would be dramatic. But that's a big if. Near the speed of a light, the effect would be dramatic. At 90% of the speed of light, time would pass at about 43% of the normal rate for the traveller. 10 years on the ship would correspond to about 23 years on Earth. At 99% of the speed of light, 10 years on the ship would correspond to about 70 years on Earth. At 99.9%, 10 years on the ship would correspond to about 224 years on Earth. The numbers get more extreme the closer you get to light speed. But reaching near light speed takes enormous energy. This is the practical barrier. To accelerate even a small spacecraft to a significant fraction of the speed of light would require energy resources we don't currently have. The faster you want to go, the more energy you need, and the relationship is steep. As you approach the speed of light, the energy required approaches infinity. Light speed is a barrier, not in the sense that it's a wall you might break through, but in the sense that it's a limit built into the geometry of space-time. Time dilation doesn't require a machine, it doesn't require technology, it only requires the right conditions. Put a clock in motion at high speed, or place it in a strong gravitational field, and time will pass differently for it. Nature does the rest. If you could travel very fast and return, you could arrive in Earth's future. You would step out of your spacecraft into a world that had aged more than you had. This is sometimes called the twin scenario in discussions of relativity. The travelling twin experiences less elapsed time than the stay-at-home twin. Imagine two twins, identical in age. One stays on Earth. The other boards a spacecraft, accelerates to a significant fraction of the speed of light, travels for a while, then turns around and comes back. When they reunite, the travelling twin is younger, not by magic, not by suspended animation, but by the geometry of their paths through space-time. The effect comes from geometry of space-time paths, not from trick clocks. In relativity, your path through space-time matters. Two different paths between the same two events can have different lengths in time. This is counterintuitive because in ordinary space, the straight line is the shortest distance. But in space-time, the straight line, the path of the stay-at-home twin, is actually the longest in terms of elapsed time. The travelling twin's path, which involves acceleration and high speed, is shorter in terms of elapsed time. Forward time travel is therefore a natural feature of physics. It's not science fiction. It's science fact, confirmed by experiments and observations. Just one more small fact, and then we drift. Gravity is not just a force in relativity. It's curvature of space-time. This is one of the central insights of general relativity. In Newton's view, gravity was a force that acted at a distance. Massive objects attracted each other across empty space. Einstein reimagined gravity. In his view, mass and energy don't pull on each other. Instead, they curve the fabric of space-time itself. Mass and energy tell space-time how to curve. Curved space-time tells matter how to move. Objects follow the straightest possible paths through this curved space-time, paths called geodesics. What we perceive as the pull of gravity is actually objects following the natural contours of curved space-time. It's like rolling a ball across a trampoline that has a heavy weight in the middle. The ball doesn't move in a straight line because the surface itself is curved. Time can run slower, deeper in a gravitational well. The stronger the gravity, the more space-time is curved, and the more time is affected. This means time passes differently at different altitudes. Clocks at higher elevation tick slightly faster than clocks lower down. The difference is tiny but measurable with precise clocks. Atomic clocks, which keep time using the vibrations of atoms, are sensitive enough to detect this effect even over height differences of just a few meters. The difference is tiny but measurable with precise clocks. In fact, one experiment placed two atomic clocks on tables at different heights in the same laboratory, separated by less than a meter vertically. The higher clock ticked faster. The difference was minute, but it was there. This confirms Einstein's prediction. Gravity affects time. Black holes represent extreme gravitational curvature. A black hole forms when matter collapses into a region so small and dense that space-time curves back on itself. The boundary of a black hole, called the event horizon, marks the point of no return. Inside the horizon, space-time is so curved that all paths lead inward. Even light cannot escape. Near a black hole, time effects become intense compared to far away. From far away, objects near a horizon appear slowed in a sense. If you watch a clock fall toward a black hole, you'd see it tick more and more slowly as it approaches the horizon. It would appear to freeze, never quite crossing, its light red-shifted and dimmed. But that's just your perspective from far away. Locally, the traveller still experiences their own normal time. From the perspective of the falling clock, nothing unusual happens as it crosses the horizon. It just keeps ticking normally. Time behaving differently often depends on viewpoint and measurement. This is a key theme in relativity. There's no single correct perspective. Different observers see different things, and all of them are right from their own frames of reference. The person far from the black hole sees the clock slow down. The person falling with the clock sees it tick normally. Both observations are valid. Gravity can bend light, changing the path signals take. Light follows geodesics in space-time just like matter does. When space-time is curved by mass, light paths curve too. This is gravitational lensing. When paths change, the story of when can look surprising. Light from a distant object can take different curved paths around a massive object in the foreground, arriving at different times. The same event can appear to happen multiple times, separated by days or years, because the light took different routes. Just one more small fact, and then we drift. Seeing is already a form of looking into the past. This is such an ordinary fact that we rarely think about it. But it's profound. Light takes time to travel from an object to your eyes. When you see something, you're not seeing it as it is right now. You're seeing it as it was when the light left it. The moon is seen as it was about a second ago. Light takes about 1.3 seconds to travel from the moon to Earth. When you look at the moon, you're seeing it as it was a little over a second in the past. The sun is seen as it was about 8 minutes ago. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. If the sun suddenly vanished, we wouldn't know for 8 minutes. For 8 minutes, we'd still see it in the sky, still feel its warmth, because the light and heat that left the sun 8 minutes ago would still be reaching us. Distant stars are seen years, centuries, or millennia in the past. The nearest star to our sun, Proxima Centauri, is about 4.2 light-years away. When we look at it, we see it as it was 4.2 years ago. Other stars are tens, hundreds, thousands of light-years distant. Some galaxies are seen as they were millions or billions of years ago. The Andromeda Galaxy, our nearest large galactic neighbour, is about 2.5 million light-years away. The light we see from it left Andromeda 2.5 million years ago, long before humans existed on Earth. Telescopes are therefore time-viewing devices as much as distance-viewing devices. When astronomers point a telescope at a distant galaxy, they're looking into the past. The farther you look in space, the farther back you look in time. This is how we study the history of the universe. We don't have a time machine, but we have telescopes, and light is a messenger from the past. Cosmic background light is a relic view of the early universe. The cosmic microwave background radiation is light that has been travelling through space for about 13.8 billion years, almost as long as the universe has existed. It's the afterglow of the Big Bang, stretched and cooled by the expansion of the universe. When we observe this radiation, we're seeing the universe as it was when it was only about 380,000 years old, long before the first stars formed. In a way, the universe stores its history in travelling light. Every photon carries information about the conditions where it was emitted. By collecting light from different distances, we assemble a timeline of cosmic history. Gravity can bend light paths, letting us see around massive objects. This is gravitational lensing again. A massive galaxy or cluster of galaxies can act like a lens, bending light from objects behind it. This allows us to see things that would otherwise be blocked from view. This bending can create multiple images of the same distant source. Sometimes a distant galaxy appears in multiple places in the sky because its light has taken different paths around a foreground mass. Different light paths can arrive at different times, like delayed echoes. If the distant source changes, like a supernova, exploding, we might see the explosion multiple times, each image appearing days or weeks apart as the light from different paths reaches us. Just one more small fact, and then we drift. A wormhole is a hypothetical shortcut connecting two distant regions of space-time. Imagine space-time as a sheet of paper. 2 points on the paper might be far apart if you measure the distance along the surface. But if you fold the paper so the 2 points touch, they're suddenly close. A wormhole would be like poking a hole through the folded paper, creating a direct connection. Wormholes appear in some solutions to Einstein's equations. Being a mathematical solution doesn't guarantee physical existence. Einstein's equations describe how space-time can be curved by mass and energy. They allow for a wide variety of shapes and configurations. Some of those configurations include wormholes. But just because the equations allow something doesn't mean nature makes use of it. Many wormhole ideas require exotic conditions to stay open. Exotic matter is a name for unusual energy properties, not a confirmed substance. To keep a wormhole open, you'd need something with negative energy density or negative pressure. This is sometimes called exotic matter. Such matter has unusual properties. We have quantum effects that can create tiny amounts of negative energy in limited situations, but scaling that up to hold open a traversable wormhole is pure speculation. If a stable wormhole existed, it might reduce travel time between places. Instead of flying across the galaxy at slower than light speeds, you could step through a wormhole and arrive instantly or nearly so. Some discussions suggest wormholes could also connect different times. If one mouth of the wormhole is accelerated to high speed or placed in a strong gravitational field, the two mouths could become desynchronized in time. Turning a wormhole into a time machine is a speculative concept. The idea is that if the two mouths of a wormhole are separated in time as well as space, you could enter one mouth and exit the other at a different time. The key issue is whether it would create a loop in time. A loop in time is often called a closed time-like curve. It's a path through space-time that loops back on itself, so you could theoretically travel into your own past. Closed time-like curves appear in certain theoretical space-time models. They're allowed by the mathematics of general relativity under certain conditions, but their physical existence is questionable. Physicists debate whether nature prevents them. Some believe there's a principle, sometimes called chronology protection, that forbids closed time-like curves. Even if the math allows it, reality might forbid it. The universe might have rules we haven't discovered yet, rules that prevent time loops from forming. Or perhaps the conditions required for a time loop are so extreme that they can never be met in practice. This is an open question. It's one of the deep mysteries still being explored. Just one more small fact and then we drift. Time travel paradoxes are puzzles about cause and effect. They're thought experiments designed to explore what would happen if backward time travel were possible. The grandfather paradox asks what happens if you prevent your own existence. Imagine you travel back in time and intentionally or accidentally prevent your grandparents from meeting. Then your parents would never be born, and neither would you. But if you were never born, you couldn't travel back in time to prevent your grandparents from meeting. It's a logical loop, a contradiction. The paradox highlights conflicts between free action and consistent history. If you can travel backward in time, do you have free will to change events? And if you change events, how can history remain consistent? The bootstrap paradox imagines information or objects with no clear origin. Suppose you travel back in time and give Shakespeare a copy of his plays. Before he writes them, he publishes them as his own. Years later, you find the plays in a library, take them back in time, and give them to Shakespeare. Where did the plays come from? They exist in a loop with no origin. These paradoxes show why backward time travel is complicated. They reveal tensions in our understanding of causality. One proposed idea is self-consistency. In this view, history can't be changed into contradiction. If you travel back in time, any actions you take must be consistent with the history that already happened. You were always part of the past. You can't change it because you were already there. Events might allow loops, but only consistent ones. In self-consistency, the universe conspires to prevent paradoxes. Perhaps every time you try to prevent your grandparents from meeting, something goes wrong. You miss the train. You lose your nerve. The universe, in a sense, protects its own consistency. Another idea involves branching timelines, often linked to interpretations of quantum theory. In this view, when you travel back in time, you create a new branch of reality. You can change events in this new branch without affecting the original timeline. Branching timelines are not confirmed as a mechanism for time travel. They arise from certain interpretations of quantum mechanics, but those interpretations are themselves debated. Many physicists suspect chronology protection, that nature blocks time loops. That backward time travel, even if allowed by the math, is forbidden by some deeper principle. Chronology protection is a hypothesis, not a proven law. The most grounded result remains. Forward time travel via dilation is real. We've measured it. We've confirmed it. We use it in technology. Backward time travel remains in the realm of speculation, interesting to think about, fun to explore in thought experiments, but not established science. And that's okay. Not every question has an answer yet, and not every idea in mathematics corresponds to reality. Just one more small fact, and then we drift. Memory is sometimes called mental time travel. This isn't literal time travel, but it's a useful metaphor. When you remember an event from your past, your brain reconstructs that moment. You revisit it internally. You experience a version of the past filtered through your mind. Imagination is another form, simulating possible futures. When you plan ahead, when you daydream, when you worry about tomorrow, you're mentally traveling forward in time, exploring scenarios that haven't happened yet. Your brain blends past and prediction to create a stable now. Your sense of the present moment is actually a construction. Your brain takes information from the recent past, combines it with expectations about the near future, and presents it to your conscious mind as now. This happens continuously, seamlessly, without you noticing the seams. The feeling of time speeding up or slowing down can change with attention. When you're bored, time seems to crawl. When you're engaged, it seems to fly. This is a subjective experience, not a change in the actual rate of time, but it's a reminder that our perception of time is flexible. In quiet rooms, the mind can notice time more sharply. Silence and stillness make us more aware of the passage of moments. Without distractions, we feel time flowing. Sleep is a reset that helps the brain file time into gentler order. During sleep, your brain processes memories, consolidates experiences, and clears away the clutter of the day. When you wake, time feels fresh again. You don't need to chase the future. It arrives on its own. Every second carries you forward effortlessly. You don't have to push time. It flows whether you pay attention or not. The universe has carried time forward for billions of years without your help. It will continue to do so. Stars age, galaxies drift apart, the cosmos evolves, all without any effort on your part. Tonight, your only job is to rest while the seconds drift by. You're already travelling through time. You always have been, and you always will be, until the very end of your journey. And if time is a river, you can let it hold you, softly, until sleep comes. You don't have to swim. You don't have to fight the current. You can float gently, carried forward by the natural flow of moments. Time isn't an enemy. It's not something to conquer or escape. It's simply the medium in which you exist, the fabric of your experience. Just one more small fact and then we drift. As you lie there, in the quiet of your room, time is passing. Each breath marks a moment. Each heartbeat is a step forward. The universe around you is vast and ancient, filled with galaxies and stars, black holes and nebulae, all moving through space-time according to the same laws that govern your own existence. And those laws are strange and beautiful. They tell us that time is not absolute, that your now is not the same as someone else's now, that the faster you move, the slower your clock ticks, that gravity bends time as well as space, that the past is visible in the light from distant stars, that the future is always arriving 1 second at a time whether you're ready or not. They tell us that the universe is more flexible than we once thought, that space-time can stretch and curve, that different paths through the cosmos can have different lengths in time, that forward time travel is real, confirmed, measured, that backward time travel is a question mark, a puzzle, a possibility that lives in equations but not yet in reality. And they tell us that understanding these things doesn't require fear or anxiety. You can learn about black holes without falling into one. You can think about time dilation without needing a spaceship. You can explore the paradoxes without getting lost in them. Science is a way of asking questions and finding answers, slowly and carefully, one fact at a time. Tonight the facts have been gentle. They've described a universe that is strange but not hostile, complex but not incomprehensible. The universe operates according to rules, and those rules can be understood. Einstein figured out relativity with thought experiments and mathematics, sitting at a desk imagining how things would look if you rode on a beam of light. You don't need to be Einstein to appreciate what he discovered. You just need to be curious, willing to think about things from new angles, ready to let go of assumptions that seem obvious but turn out to be wrong. The assumption that time is the same for everyone, everywhere, always. The assumption that the past is the past and can't be touched. The assumption that the future is separate from the present. Relativity replaced those assumptions with something richer. It gave us a space-time where past and future are woven together with the present, where time and space are two aspects of the same thing, where the geometry of your path determines how much time you experience. And it did this not through mysticism or philosophy, but through careful reasoning and experimental confirmation. The GPS satellite confirms it every day. The atomic clock confirms it every measurement. The astronaut confirms it every mission. The telescope confirms it every observation. Time is flexible. Time is relative. Time is part of the structure of the universe, not just a number on a clock. And here's the comforting part. You don't have to do anything with this knowledge. You don't have to build a time machine. You don't have to solve the paradoxes. You don't have to travel to the stars. You can simply know that the universe is richer and stranger than it appears, and that knowledge can be soothing in its own way. It's soothing because it means reality is not mundane. There are depths to explore, mysteries to ponder, wonders to appreciate, and it's soothing because you're part of it. You exist in space-time, you travel through time every moment. The same laws that govern galaxies also govern you. You're made of atoms that were forged in stars, and those atoms move through space-time according to Einstein's equations. You are, in a very real sense, a piece of the universe experiencing itself. And tonight, this piece of the universe is getting ready to sleep. The brain that ponders time dilation is also the brain that needs rest. The body that exists in space-time is also the body that gets tired. And that's fine. That's natural. That's how things should be. As you settle into your bed, the world outside continues. The Earth rotates, carrying you along with it. The moon orbits the Earth orbits the sun moves through the galaxy moves through the cosmos. Everything is in motion, everything is travelling through space-time, and you're part of that great cosmic dance. But for now, your part in the dance is to rest, to let your muscles relax, to let your thoughts slow down, to let the day fade into memory. Sleep is a form of time travel in its own way. You close your eyes in the present, and when you open them, it's the future. Hours have passed without your awareness. The night has carried you forward, gently, while you were unconscious. And that's all time ever does, really. It carries you forward, gently, whether you're awake or asleep. The difference is that when you're asleep, you don't notice the journey. You skip ahead, in a sense, arriving in the morning without experiencing the hours in between. It's the most common form of time travel, the one we all do every night, and it requires no physics, no technology, no exotic matter. Just closing your eyes, just letting go, just trusting that time will continue, that the universe will keep operating, that tomorrow will arrive on its own. You don't have to worry about the grandfather paradox or closed time-like curves or chronology protection. You don't have to understand the mathematics of general relativity. You just have to be here, now, letting the moments drift past. The facts have all been told. 100 small pieces of understanding woven together into a story about time. Some of them were about forward time travel, the real kind, the kind that's been measured and confirmed. Some of them were about backward time travel, the speculative kind, the kind that lives in equations and thought experiments. Some of them were about gravity and light and the structure of space-time, and some of them were reminders. Reminders that you're already travelling through time, that the universe is already carrying you forward, that you don't need to chase the future because it's coming to you, that the past is visible in starlight and preserved in memory, that the present moment is a gift, a brief intersection of all possible paths. Time is a river. You can fight against the current, trying to swim upstream, trying to hold on to moments that have already passed. Or you can float, letting the current carry you, trusting that the river knows where it's going, and tonight the river is carrying you towards sleep, toward rest, toward the quiet darkness where time becomes irrelevant because you're not conscious to measure it. The universe has been expanding for nearly 14 billion years. It will continue to expand long after you're gone. Stars will burn out, new stars will form, galaxies will drift apart, black holes will evaporate, time will march on, indifferent to any individual, but encompassing everything. And in this vast cosmic story, you have a brief moment, a few decades perhaps, a tiny flicker in the life of the universe. But that flicker is yours. Those decades are yours. Each second, each minute, each hour is a piece of time that you get to experience. And some of those pieces, like right now, are meant for rest, not for striving or achieving or understanding, just for being, just for breathing, just for letting the day dissolve. The science of time travel has been explored, the questions have been asked, the answers, such as they are, have been given. Forward time travel is real but requires conditions we can barely achieve. Backward time travel is theoretically possible under certain speculative circumstances, but remains unproven and fraught with paradoxes. And the time travel we do every day, the simple forward march of moments, continues regardless. You age, the world changes, seasons pass, years accumulate, and through it all, time flows at its own pace, shaped by gravity and motion but never stopping, never reversing, always carrying everything forward into the future. This is the rhythm of reality. This is the beat to which the universe dances. And now, with all the facts laid out, with all the concepts explained, with all the gentle details provided, there's nothing left to do but drift. The intellectual journey is complete. The story has been told. The science has been shared. What remains is the simple physical need for sleep, the biological imperative that tells you it's time to stop thinking and start resting. Your body knows what to do. It's done this thousands of times. It knows how to relax muscles, how to slow breathing, how to quiet the mind. It knows how to transition from wakefulness to sleep, from conscious thought to unconscious rest. You don't have to control the process, you just have to allow it. And as you allow it, as you feel yourself beginning to drift, remember that you're not alone in this. Billions of people across the planet are doing the same thing. Some are already asleep, some are just lying down, some are fighting sleep, trying to stay awake a little longer, but eventually all of them will surrender. All of them will let time carry them into the night, because sleep is inevitable, rest is necessary, and the universe, which has been carrying you through time since the moment you were born, will continue to do so while you're unconscious. It doesn't need your attention. It doesn't require your awareness. It just keeps moving, keeps flowing, keeps being. Time travel, the phrase we started with. We've explored what it means, what's real, what's speculative. We've learned that time is stranger than we thought, more flexible, more relative. We've seen that the universe allows different observers to experience time differently. We've considered paradoxes and wormholes and closed time-like curves. But in the end, the most important thing is simple. You travel through time every moment of your life. You're doing it right now, and tonight as you drift off to sleep, you'll continue to do it, moving forward 1 second at a time, 1 breath at a time, until morning comes and you wake up in the future, in tomorrow, in the next chapter of your journey. The universe is vast. Time is deep. The questions are endless. But sleep is simple. Sleep is easy. Sleep is what comes next. So let the science fade. Let the facts blur. Let the wonder remain, but let the thinking stop. You've learned enough for one night. You've travelled far. Enough through these ideas. Now it's time to travel through the hours of darkness. To let time do its work while you rest. To trust that when you wake, the world will still be here, still turning, still moving through space-time according to the same laws that have governed it for billions of years. Just one more small fact and then we drift. Actually, there are no more facts. The 100 have been given. The outline has been followed. The journey through the science of time travel is complete. What's left is not information but experience. The experience of lying in a quiet room. The experience of feeling your body settle. The experience of noticing your breath slow and steady. In and out, in and out. Each breath is a moment. Each moment is a step forward through time. You're not thinking about time dilation anymore. You're not worrying about paradoxes. You're just breathing, just being, just existing in the eternal now that is always present, always moving, always becoming the next moment. And that's enough. That's all you need. The universe doesn't require you to understand it in order to participate in it. You can simply be part of the flow, part of the great cosmic river of time, carried along with everything else, stars and galaxies and atoms and thoughts, all moving together into the future. Sleep is close now. You can feel it at the edges of your awareness, a gentle darkness waiting to embrace you. You can feel your thoughts becoming less distinct, less focused, less insistent. The need to understand is fading. The need to question is quieting. The need to stay awake is dissolving. What remains is peace. What remains is rest. What remains is the simple animal comfort of lying down at the end of the day, safe and warm, ready to let consciousness go for a while, ready to travel through the night without effort, without awareness, without resistance. The universe will keep moving, time will keep flowing, and you'll keep travelling forward, even in sleep, even in dreams, even in the deep unconscious rest that restores your body and mind. When you wake, you'll have arrived in tomorrow. You'll have completed another journey through time, the easiest and most natural kind. But that's hours away. Right now, there's only this moment, this breath, this feeling of letting go. The science of time travel has been explained, explored, and absorbed. The story has been told in a gentle voice, at a slow pace, with care for your comfort and peace. And now, with nothing left to say, with no more facts to share, With the outline complete and the word count reached, it's time to simply be quiet, to let silence fill the space, to let sleep approach at its own pace, to trust that the journey through time will continue whether you're awake to witness it or not. So rest now. Let your eyes close. Let your breathing deepen. Let time carry you forward, gently, softly, into the peaceful darkness of sleep. The universe is taking care of the details. You don't have to do anything except drift, just drift and sleep. The next story is about to begin. Please relax and enjoy.